Every single day, the United States alone extracts over 9 million barrels of oil. A single barrel holds nearly 159 liters. Now multiply that by thousands of wells across the planet. But have you ever stopped to consider what oil actually is and how it is formed? This isn't just a black liquid. It is the result of immense geological forces acting over millions of years deep within the earth. Oil is born from the remains of ancient life, transformed by pressure and heat into a liquid hydrocarbon. And from there, the modern story begins. A high-stakes hunt, deep earth drilling, and the incredible process that turns this primordial substance into the fuel that moves our world. It's expected that the average daily oil output in the U.S. will soon reach 9.9 million barrels. But what exactly is this substance we call oil? The process of its formation is a slow, powerful saga that unfolds over geological time. It begins with the accumulation of organic material, the remains of ancient plants and animals at the bottom of seas and lakes. Over millions of years, these remains are buried under layers of sediment. Under the immense pressure and heat, this organic matter transforms into a waxy substance called kerogen. Further heating, in a temperature window between 60 and 150 degrees Celsius, triggers the thermal breakdown of kerogen, creating liquid hydrocarbons. And that is what oil is, the distilled essence of ancient life. Once formed, this oil migrates through porous rock until it reaches a geological trap, a structure that blocks its path. Here, it accumulates, forming a reservoir. To find these hidden reservoirs, we must first understand the earth beneath our feet. This is the world of geological surveying, one of the most complex and expensive stages of the process. Scientists use satellite imagery, magnetometers, and seismic waves. Seismic surveying is particularly spectacular. Controlled underground explosions are triggered to send shock waves deep into the earth. By reading the echoes, geologists can map the subterranean landscape and identify potential traps. When a promising zone is identified, the drilling begins. A land or offshore rig becomes a giant mechanical creature operating day and night without pause. The drill string, steel pipes with a cutting bit at the end, bites into the earth, rotating at up to 200 revolutions per minute. A special drilling fluid is pumped down to lubricate the bit and carry rock cuttings back to the surface. A modern well can reach depths of 3 to 5 kilometers, and in some cases 10 or even 12. In Texas or Saudi Arabia, wells are drilled over 8 kilometers long, often with a significant horizontal section to maximize contact with the reservoir. A single drilling operation can cost tens of millions of dollars with no guarantee of success. But when a well strikes oil, it begins its journey to the surface, either under its own pressure or with the help of powerful pumps. Saudi Arabia is one of the world's oil titans. In February, the kingdom was producing nearly 9 million barrels per day, and its position is only set to strengthen, as Saudi Aramco has recently discovered 14 new oil and gas fields. Once the well is completed, the extraction phase begins. In a rich reservoir, the natural pressure is enough to force the oil to the surface. This is known as a gusher, and while it looks impressive, it's now considered an outdated and dangerous method. Modern wells are fitted with complex valve systems known as Christmas trees that allow for precise control of the flow. The crude oil emerges and is sent to a processing facility where it is separated from natural gas, water, sand, and other impurities. This often happens right at the well site. The separation is a fascinating process. The mixture enters a large sealed vessel where gravity takes over. The lighter gas rises to the top while heavy water and sediment sink to the bottom. Sometimes, water is trapped in the oil as a microscopic emulsion, which is harder to separate. In this case, chemical de-emulsifiers are added to break it down. To maintain pressure in an aging reservoir, secondary recovery methods are used. Water or gas is injected into the formation through other wells to push the remaining oil towards the production well. These techniques can allow up to 60% of a reservoir's oil to be recovered. The average modern well in the U.S. produces between 500 and 1,500 barrels per day. A single barrel is 159 liters. Multiply that across thousands of wells and you begin to grasp the true scale of this global operation. Crude oil itself is a complex cocktail of hundreds of different hydrocarbons. To turn it into petrol, it must undergo a series of technically demanding stages at a refinery. It all starts with fractional distillation. The crude oil is heated to between 350 and 400 degrees Celsius and fed into a tall distillation column. The various components of the oil vaporize and rise to different heights inside the column before they cool, condense, and are drawn off. The petrol fraction is one of the lightest, and it's typically collected at a temperature between 40 and 200 degrees. But this initial distillation only yields about 15 to 20% petrol. To increase the yield, a process called cracking is used. This breaks down long, heavy hydrocarbon molecules into shorter, more valuable ones. The most common method is fluid catalytic cracking, where heavy fractions are heated to nearly 1,000 degrees in the presence of a catalyst. This allows for a much higher yield of petrol from the heavier residues. Hydrocracking, which uses hydrogen under high pressure, is also used. Ultimately, the petrol yield from a single ton of crude oil can be pushed as high as 40 or 50%. The petrol produced so far, however, has a low octane rating. To fix this, it undergoes reforming, a process that restructures the molecules at high temperatures using a platinum catalyst. In the final stage, additives are blended into the petrol to improve its properties: anti-corrosion agents, anti-knock compounds, and detergents. This ensures engine longevity, reduces harmful emissions, and improves efficiency. A single modern refinery can process up to 400,000 barrels of crude oil every single day. The sheer volume is staggering, especially when you consider that the daily petrol consumption in the U.S. alone is around 1.4 billion liters. A river of ancient life, powering the modern world.
The fastener industry is a true empire worth over $90 billion annually. And its flagship products? Massive bolts and nuts that hold our entire industrial infrastructure together. They're not just chunks of steel with machined threads, they're the result of a complete process involving metallurgy, high-pressure forging, heat treatment, and incredibly rigorous mechanical testing. One tiny deviation in material quality, shape, or tightening force can render an entire joint unsafe. In this video, we're going inside the production line that creates giant hex bolts and nuts to show how raw steel transforms into the mechanical foundation of the modern world. The production process for heavy-duty bolts and nuts begins with one fundamental stage: cutting raw blanks. Large diameter steel bars rolled from high-strength alloy steel are fed into industrial cutting machines and divided into segments with precisely controlled length and weight. Modern cutting systems use hydraulic shears or powerful industrial saws, producing clean square cuts that don't distort the metal's internal structure. Throughout the cutting operation, coolant is sprayed directly onto the contact zone to reduce temperature, minimize friction, and wash away metal chips. This maintains cutting tool stability and ensures the blank surfaces remain clean and free from thermal damage. Typically, bolt blanks are roughly twice as long as nut blanks, because bolts require additional material to forge the load-bearing shaft and head in a single production run. During one shift, each cutting machine can process thousands of bolt and nut blanks. Each cut takes just a few seconds, yet the allowable tolerance is extremely tight, because the final shape and mechanical strength of the product depend entirely on the initial dimensions of these blanks. After the blanks are cut, the bolts and nuts move to the heating stage, but the way heat is applied to each component isn't quite the same. For nuts, the entire steel blank feeds into a continuous furnace and is uniformly heated to a temperature range of 1900 to 2100 degrees Fahrenheit. Heating the entire body allows the blank to reach a fully plastic and uniform state. So during forging, the metal can flow evenly inside the die and form a solid hexagonal body before the internal hole is drilled and threads are cut. Temperature is tightly controlled to prevent surface burning while ensuring the core remains soft enough for proper forming. Bolts, however, are heated differently. Instead of heating the entire blank, only the head portion of the steel rod passes through an induction heating system. In a matter of seconds, the front end reaches forging temperature and glows bright orange-red, while the shaft behind it stays significantly cooler. This localized heating method concentrates energy exactly where the hex head needs to form, reduces overall energy consumption, and preserves the mechanical structure of the bolt shaft, which is the primary load-bearing section of the fastener. Right after reaching forging temperature, the blanks are transferred directly into the hot forging zone for shaping. For nuts, the entire evenly heated blank is placed inside a closed forging die, where a high-powered hydraulic press forces the metal to flow according to the die's shape, forming a solid hexagonal body. Under this intense compression, the metal densifies, and its crystalline grains reorganize into a tighter structure, making the steel denser and more uniform. Between each press cycle, the forging die is sprayed with a layer of high-temperature coolant and lubricant. This helps control heat, reduce friction, and protect the die surface during continuous operation. For bolts, the forging process focuses on the head section that was induction heated. The blank is positioned so the hot end sits precisely inside the die, and the press applies force, causing the metal to flow outward, forming the hexagonal head. At the same time, the die is also sprayed with the same type of high-temperature lubricant used in nut forging. When the fluid contacts the hot die, it instantly vaporizes and creates a temporary protective film. This prevents metal adhesion and ensures the bolt head forms cleanly, with sharp, clearly defined edges. Right after forging, both the bolts and nuts are dumped straight into large steel containers for natural cooling in the open air. For big components, this cooling stage typically runs anywhere from 30 to 60 minutes, and can take even longer if the steel mass is particularly heavy. This slow cooling method prevents thermal shock, minimizes the risk of microscopic cracking, and keeps both the shape and the internal structure of the metal stable before the parts move on to the next production stages. Once fully cooled, the bolts and nuts are transferred to the surface cleaning stage. At this point, they're typically loaded in bulk into rotating drum cleaners or vibratory tumbling machines. The rotating drum moves slowly and steadily, creating mechanical friction across the entire surface of the bolts and nuts. This process sharpens the hex edges and leaves the metal surface clean, dry, and uniform. In large-scale production lines, each batch can handle anywhere from a few hundred to several thousand parts at once. Tumbling time usually ranges from a few minutes to several dozen minutes, depending on the size of the parts and the level of oxide scale stuck to their surfaces. Once the surface is cleaned, the bolts and nuts move to the identification marking stage. For nuts, markings are stamped directly onto the hexagonal body, while for bolts, markings are placed on the top face of the head. These symbols indicate the strength grade, technical standards, and manufacturer of each part. They function as an official ID card, mandatory for bolts and nuts to be approved for use in industrial structures, heavy machinery, and large-scale construction projects. Once they've achieved their final shape and received their identification markings, bolts and nuts enter one of the most critical stages of the entire process: thread machining. The threading process for bolts typically begins with a light finishing turn on the shank to achieve a precise diameter and a sufficiently smooth surface. On the lathe, the bolt is firmly clamped and rotated at a steady speed, while the cutting tool simply glides over the surface to correct dimensions before threading. After this, the workpiece is transferred to a thread rolling machine, where 2 or 3 thread rolling dies, engraved with the precise thread profile, press against the shank under high pressure. Thread rolling is a cold-forming process that doesn't remove material but rather deforms the surface of the shank, creating threads through plastic flow of the metal. This produces stronger threads with improved fatigue resistance compared to threads cut by a cutting tool. For nuts, threads are created through the tapping method. First, a specialized drill bores a vertical hole through the center of the hexagonal body. Then a tap, a rotating cutting tool with external threads, is inserted into the hole. As it advances, the cutting edges of the tap shave material from the hole wall, forming a precise internal thread profile. During the tapping operation, cutting fluid is continuously supplied to cool the cutting edges, lubricate contact surfaces, and flush away metal chips. Once threading is complete, both bolts and nuts move on to final quality control. First up are geometric checks: diameter, thread pitch, thread depth, concentricity, and sharpness of the thread profile. Threads must match standard thread gauges perfectly. Even the tiniest deviation means rejection. Next come mechanical tests including surface hardness, tensile strength, and torque resistance. Only after passing all these tests do bolts and nuts move to packaging. At this stage, the products are no longer semi-finished parts. They're full-fledged structural components, ready to ship to construction sites, power plants, steel bridges, or drilling rigs, where every bolt and nut will be responsible for holding together massive industrial systems. From raw steel rods through cutting blanks, heating, forging, thread cutting, inspection, and packaging, giant bolts and nuts complete a manufacturing journey that's precise down to the tiniest details. If you find this journey fascinating, hit that like button to support the video, drop a comment to share your thoughts, and subscribe to the channel to keep exploring the production lines that quietly keep our modern world running. You're holding $100 in your hand, a green piece of paper with Franklin's face on it. Light, thin, looks ordinary, but it's not paper, and it's not ordinary. This bill was printed in a building guarded better than the Pentagon. Cameras everywhere, motion sensors, armed security. Getting in there is harder than getting into Fort Knox. The paper for it was made using a secret formula: 75% cotton. 5 people in the world know the formula. Printed 3 times. Each time with different inks. Each time with precision down to a micron. One wrong stroke, and the bill is counterfeit. Checked by machines. Every millimeter scanned. Rejects burned immediately. Not even one bad bill gets out. Because if it makes it outside, someone could forge it. This piece of paper is protected better than a vault in a bank. Watch till the end. You'll learn how money is printed. And you'll never look at a dollar as just a simple piece of paper again. Texas, Cotton fields stretching to the horizon. Heat pushing 100 degrees. White cotton bolls bursting on the bushes. Combines harvesting the crop. But not all cotton makes the cut for money. Only the longest fibers. White, strong, hand-selected, shipped to the factory, Massachusetts, town of Dalton, Crane Currency Facility. They've been making paper for dollars since 1779. Nobody else in the world has the rights. The grounds are guarded around the clock. Airport-level security screening. Cameras in every corner. Cotton gets mixed with linen. Boiled in massive vats. Water added. Creates a white pulp. Rolled into thin sheets. During the rolling, red and blue fibers get woven in. Randomly. Chaotically. Impossible to replicate the pattern. First line of defense. Then a security strip gets embedded. Thin metallic thread. Glows under ultraviolet light. Water pressed out. Dried. Cut into large sheets. Every sheet inspected against the light. Checking for defects. One air bubble. Sheet gets rejected. Finished paper gets packaged. Transported under convoy. Armed guards. Armored truck. Because if someone steals this paper, they can print real money. Washington, D.C. A building with no signs. Gray, nondescript. Inside, they print money. Bureau of Engraving and Printing. Security level like a military base. Metal detectors, retinal scanners, fingerprints. Even employees can't enter without triple verification. Cell phones banned. Cameras banned. Any recording devices confiscated. Inside, printing presses the size of a bus. Each one costs $10 million. Running around the clock. Sound like a jet taking off. Paper loaded in stacks. 32 sheets per stack. Each sheet will print 32 bills. First pass, background printing. Green patterns, fine lines. Hand-drawn by engravers, for months. One mistake, start over. Lines so fine they're invisible to the naked eye. That's the second anti-counterfeiting measure. Special ink. Formula classified. Made at a different facility. Under the same level of control. Sheets pass through the printing cylinder. Come out green. Wet. Dried under infrared lamps. Every sheet inspected. Sensors scan color, density, line alignment. Precision. 1/100th of a millimeter. Thinner than a human hair. Second pass. Intaglio printing. The most important one. Franklin's portrait, the numbers, the text, all of it printed under massive pressure. 3 tons per square centimeter. The ink gets pressed into the paper. Run your finger across it, you feel the texture. That's the main security feature. Impossible to fake. Regular printers can't do this, even professional ones. You need a special machine. There are 10 of them in the world, and they're all here. The printing cylinder is covered in microscopic grooves. The design is laser engraved. Precision, 5 microns. That's 10 times thinner than a human hair. The cylinders get replaced every year. The old ones are destroyed, melted down, turned into scrap metal. So nobody can recover the design. Sheets pass through the machine. Come out with Franklin's portrait. Sharp numbers, raised lettering. Another inspection. Machines scan every detail. Compare it to the standard. If even 1 pixel is off, the sheet gets rejected. Rejects are set aside separately. Shredded at the end of the day. Burned. The ash dissolved in acid. Even the ash from dollars can't just be thrown away. Third pass, serial numbers. Every bill gets a unique code, 11 digits and letters. This combination doesn't exist anywhere else in the world. Printed in green ink, right side and left side. The numbers must match perfectly. The machine checks. If left and right don't match, rejected. Right then, they print the Treasury seal, green circle, and the Federal Reserve Bank seal, black. The letter shows which bank issued the bill. All of this happens in 3 seconds. The sheet runs through the machine, comes out with numbers and seals. Final inspection, the toughest one. Machines scan the bills under ultraviolet light, under infrared light, under magnification. They check 15 parameters: color, texture, security strip, watermark, line alignment, ink density, size, centering, numbers. Any deviation, rejected. Rejection rate, 3%. Out of every 1,000 bills, 30 get destroyed. Good sheets go to cutting. The rest, into the shredder. Cuts into individual bills. Precision, 1. Cuts into individual bills. Precision, 1/10 of a millimeter. If even one bill is cut crooked, the entire sheet is scrapped. Bills drop into a tray. A robot picks them up, counts them. 100 bills per stack. Wraps them in paper. 100 stacks per block. $10,000 in a single block. Blocks get wrapped in film, sealed, stamped with the date. Serial number, quantity, loaded into safe containers. Metal ones. Locked with 3 separate locks. 3 different people hold the keys. One person can't open it. Containers get loaded into an armored truck. Armed guards. 2 escort vehicles. Driven to the Federal Reserve Bank. There they're unloaded into the vault. Underground. Walls 3 feet thick. Steel reinforced concrete. The bills sit and wait until some bank requests them. Then they're pulled out. Counted, packaged, shipped off. Your local bank orders fresh bills. The request goes to the Federal Reserve. From there, they ship a container. Again, under guard. Brink's armored truck. 2 armed guards. GPS tracker, dispatch communication. Any route deviation triggers an alarm. They arrive at the bank, unload into the vault, check the seals. Open the container, count everything. By hand and by machine. The amount must match to the cent. Some bills go into ATMs. An operator loads the cassettes, $4,000 in one cassette. Inserts it into the ATM. Closes it up, a TM's ready. You walk up, insert your card, enter your PIN, request $100. Inside, rollers activate. Grab one bill, sensors check it. If the bill's wrinkled or torn, the ATM won't dispense it. Takes the next one, feeds it through the slot. You grab it, fold it into your wallet, and walk away. Never thinking about the journey that piece of paper took. From a cotton field in Texas to your wallet. Secret paper, triple printing, 15 inspections, armed guards at every stage. Now you know. This bill isn't just paper. It's the most protected document in the world. It was printed by people who passed security clearances, working on machines worth $10 million, under cameras and sensors. Any mistake, and the bill is destroyed, burned, dissolved in acid, because even a defective bill in the wrong hands is a threat. Someone could study it, understand the technology, try to counterfeit it. That's why the security is so tight. You'll never look at a $100 bill like ordinary paper again, because now you know it has 300 years of technology encrypted in it. Red fibers in the paper are randomly placed. The security strip glows under ultraviolet light. Franklin's portrait is pressed under 3 tons of pressure. Microlines thinner than a hair. Serial numbers unique. This bill is impossible to counterfeit, even if you really try, because it wasn't made to be beautiful. It was made to protect money from counterfeiters, and it works. What if I told you there's a metal that flows like water at room temperature, killed thousands of workers during the colonial era, and without which gold mining would be impossible? a metal that vaporizes at 1100 degrees Fahrenheit and condenses back into liquid silver? Every year, the world produces around 1,300 tons of mercury, but that's nothing compared to historical scales. Over the last 500 years, humanity has extracted about 1 million tons of mercury from the Earth's depths. Half of that million was used before 1925. Mercury is obtained from red ore, cinnabar, by heating it to 900 to 1100 degrees Fahrenheit. During this process, mercury sulfide breaks down, releasing mercury vapors and sulfur dioxide gas. China dominates production, 95% of the world's mercury. In 2022, China produced 2,000 tons of mercury. A standard flask holds 76 pounds of mercury. These were the exact flasks used to ship it to gold mines during the gold rush. Stick around till the end. You'll discover a secret that even those who work with this metal won't talk about. Picture an underground mine somewhere in China, Kyrgyzstan, or Mexico, the world's biggest mercury producers. Deep beneath the surface, in the dim glow of miners' lamps, red streaks appear in the rock. This is cinnabar, mercury sulfide, a bright red mineral that humanity has known for thousands of years. The ancient Romans mined it both as a pigment and for mercury. The ancient Egyptians were using mercury as far back as 1500 BC. Greek philosopher Aristotle in 350 BC described how cinnabar was heated to extract mercury for religious ceremonies. Cinnabar forms in veins associated with volcanic activity and hot springs. About 90% of deposits require underground mining with tunnels. The remaining 10% can be extracted through open-pit methods. Cinnabar is separated from the surrounding rock through drilling and blasting or using powerful machinery. The ore is hauled out of the mine on conveyor belts or in trucks. Because cinnabar is a relatively concentrated ore, it can be processed directly without intermediate steps to remove waste rock. The ore is first crushed in one or more cone crushers. A cone crusher consists of an inner cone rotating on an eccentric vertical axis inside a stationary outer cone. When ore is fed into the top of the crusher, it gets squeezed between the two cones and breaks into smaller pieces. For concentrating low-grade cinnabar with a specific gravity of 8 to 8.2, gravity and flotation methods are used. Grinding to -48 mesh is the economically viable liberation point for the mineral. Some operations use mineral jigs to recover coarse heavy mineral and any metallic mercury that might be present in the ore. Flotation with one or more cleaning stages is used to produce a high-grade concentrate. It's not uncommon to obtain concentrates containing 40 to 50% mercury from ores containing 5 to 15 pounds of metal per ton. The concentration ratio is therefore high. The dewatered concentrate from flotation is combined and stored for roasting and recovery of metallic mercury. Now comes the most critical and dangerous stage, roasting. Cinnabar concentrate gets loaded into specialized furnaces. These can be multi-hearth furnaces, where ore mechanically moves down through a vertical shaft from one level to another via slowly rotating rakes. Or rotary kilns, where ore tumbles along the length of a long rotating cylinder, tilted a few degrees from horizontal. Either way, heat comes from burning natural gas or other fuel at the bottom of the furnace. Heated cinnabar reacts with oxygen in the air at temperatures ranging from 930 to 1,110 degrees Fahrenheit. A chemical reaction occurs. Mercury sulfide breaks down into sulfur dioxide gas and mercury vapor. Mercury rises as vapor. This is called roasting. Mercury vapors rise upward and exit the furnace along with sulfur dioxide, water vapor, and other combustion products. Significant amounts of fine dust from the crushed ore also get carried away and must be separated and captured. Next comes condensation. Hot gases containing mercury vapor pass through a cooling system. A condensation column is used, a special device where the vapors cool down and mercury condenses back into liquid metal. Pure mercury separates from sulfur in this process and evaporates easily. The condensation column collects the liquid metal. Thanks to mercury's high specific gravity, impurities gather on the surface and can be easily removed. The liquid mercury gets poured into standard iron flasks. Each flask holds 76 pounds of mercury. That's the standard unit of sale. These exact flasks shipped mercury to gold mines during the gold rush in California and Nevada in the 18th and 19th centuries. The process is simple in essence, with one drawback: toxic fumes. If roasting is done incorrectly, mercury vapors, which are highly toxic, can get released into the atmosphere. This was catastrophic for workers in the colonial era. The history of mercury production is full of tragedies. In 1564, cinnabar mining began in Huancavelica, Peru. With a local source of mercury, the amalgamation process was adopted for refining silver in Potosi, Bolivia, in the early 1570s. As a result, massive quantities of mercury were released into the environment. Between 1564 and 1810, approximately 17,000 tons of mercury vapor were released into the atmosphere in Huancavelica and 39,000 tons in Potosi. In 1604, an advocate for indigenous people described how fumes, dust, and candle smoke in the mine caused coughing and Huancavelica disease, and argued that forcing people to work in mercury mines meant sending them to a slaughterhouse. In 1630, a contemporary described the mines as a living image of death and a dark shadow of hell. The Jesuit José de Acosta, around 1590, wrote about the roasting process. If the smoke or fumes reach the people opening the pots, they get mercury poisoning and die, or are left in very poor condition or lose their teeth. The largest mercury deposit in history? Almaden in Spain. It was worked from Roman times until 1989, the world's biggest producer. In 2000, Almaden yielded 236 tons of mercury. Other major deposits: Khyder in Kyrgyzstan, 550 tons, Algeria, 240 tons. During World War II, mercury production was critical. Mercury fulminate was essential for bullet primers, and the biggest producing region in Spain was under dictator Franco's control. The U.S. ramped up domestic production from 1941 to 1944. The price per flask during the war years averaged around $380 in 1960 prices. Today, global mercury production has plummeted. In 2016, they produced 4,500 tons, but in 2023, just 1,200 tons. China dominates with 95% of world production, 1,000 tons in 2023. Mercury has diverse applications, but its use is declining due to toxicity. Mercury easily forms amalgams with other metals, making it useful for extracting gold and silver. Much of the incentive to develop mercury deposits in the United States arose after the discovery of gold and silver in California and other western states in 1800. When mercury mixes with gold slurry, it triggers a reaction that separates gold from ore. This amalgam is then heated to vaporize the mercury and leave behind gold nuggets. Artisanal and small-scale gold mining is the largest source of anthropogenic mercury emissions, accounting for 38% of global releases. Other applications include chlorine and caustic soda production in mercury cell electrolysis plants. Until recently, this was a major consumer. In 2023, only one such facility was operating in the U.S. electrical devices: fluorescent and mercury vapor lamps, mercury batteries, switches, and relays. Measuring instruments: thermometers, barometers, pressure gauges. Dental amalgam, a mixture of mercury with silver and other metals for fillings. But because of its high toxicity, mercury use has dropped sharply over the last 20 years. Inhaling mercury vapor is especially dangerous for the kidneys, central nervous system, respiratory and cardiovascular systems. Inhaling mercury vapor also causes neurobehavioral disorders like hand tremors and mental impairment. Exposure to other forms of mercury, particularly methylmercury, which accumulates in fish, can also lead to kidney problems, lung issues, and central nervous system damage, as well as arthritis, reproductive problems, memory loss, psychosis, and in some cases, death. The United States banned the export of elemental mercury on January 1, 2013, under the Mercury Export Ban Act of 2008. Global mercury resources are estimated at around 600,000 tons, mostly in China, Kyrgyzstan, Mexico, Peru, Russia, Slovenia, Spain, and Ukraine. And so, having traveled from red cinnabar ore through roasting at 1100 degrees Fahrenheit, through evaporation and condensation, through the tragedies of thousands of workers in the colonial era, through the gold rush and world wars, emerges a liquid metal that flows at room temperature, without which gold mining would be impossible, but which has killed more people than any other metal in human history.
Every year in Dubai alone, over 1 million tons of asphalt are produced, and that number is constantly rising. Imagine it, tankers carrying millions of barrels of crude oil dock at Jebel Ali port. The oil is distilled in reactors at over 350 degrees Celsius, and a black, heavy residue is transformed into an advanced, elastic bitumen. Then come minerals from the mountains of Fujairah, processed at hundreds of tons per hour, blended in automated mixers, and transported in insulated trucks. This is the engineering magic that gives Dubai roads that neither melt in the sun nor crack in the night. Watch until the end, and you will discover the secret that makes this asphalt tougher than the desert itself. It all begins on the waters of the Persian Gulf, where giant tankers slowly cut through the surface, carrying millions of barrels of black gold, crude oil. They journey from Iraq, Saudi Arabia, and Kuwait. When a tanker docks at a port in the UAE, such as Jebel Ali, a process begins where men and machines work as a single organism. The oil is pumped into vast storage tanks, hidden within the industrial landscape, marking the start of its transformation. From there, it travels underground through a network of pipelines, like arteries leading to the heart of the refineries. In Jebel Ali or Abu Dhabi, it is met by a city of steel, reactors, distillation towers, and chrome columns. Here, the crude oil is heated to over 350 degrees Celsius to separate it into fractions. Lighter components, petrol, diesel, kerosene, vaporize first. The heaviest residues, the ones that refuse to vaporize even at these temperatures, are exactly what we need. This residue is fed into a vacuum distillation column, where the pressure is dropped to a minimum. What remains is bitumen, a black, viscous substance, the soul of asphalt. On its own, however, this bitumen is too thick and brittle for road construction, especially in a desert where the surface temperature can reach almost 50 degrees. So it must be modified. In special reactors, the bitumen is blended with polymer additives, plasticizers, stabilizers, and sometimes even crumb rubber. This is the bitumen modification process. The result is a material with high elasticity and resistance to UV radiation, one that won't soften under the sun or crack when the temperature plummets at night. In Dubai, a polymer-modified bitumen that meets the strict standards of the RTA, the Emirates Roads Agency, is used almost exclusively. Once the bitumen has completed its transformation, it begins the next stage of its journey, delivery to the asphalt mixing plants. The modified bitumen is transferred from the reactor into insulated storage tanks which maintain its temperature at around 175 degrees. In this liquid state, it remains perfectly uniform. It is then pumped through high-pressure sealed pipelines to the nearby plant or loaded into road tankers with special thermal containers. These tankers are built with a double-skinned steel body and a thick insulating layer. The drivers undergo special training. They must maintain a steady speed and monitor temperature sensors in real time. If the temperature begins to drop, an onboard heating system activates. At the plant, for example, the DXB asphalt factory in Dubai Industrial City, the tanker connects to the intake system. At this moment, the bitumen is hot, thick, and has a distinctive smell. It is pumped into the plant's holding tanks, where it waits to be precisely dosed. From this point on, it is no longer just a material. It is a component in a formula, where the weight, viscosity, and temperature of every ingredient will determine the lifespan of the road it is destined to become. One of the largest plants is the DXB asphalt factory. Here, the bitumen is heated to 160 degrees and mixed with mineral aggregates, gabbro, basalt, and quartz sand. Gabbro is a dark volcanic rock quarried in the mountains of Fujairah. The rock is crushed into fractions smaller than 25 millimeters, screened through vibrating sieves, dried in huge rotating drums, and then fed into the mixer. Inside, the bitumen and aggregates are combined into a hot, uniform mass known as hot mix asphalt. The temperature of the mix is 160 degrees. It must be perfectly homogeneous with a precise ratio of components. After mixing, the asphalt is transferred to insulated silos where it can be stored for no more than 6 hours. From there, it is loaded into insulated trucks for the final journey. On site, the asphalt is laid by paving machines and then compacted by rollers, first vibratory, then static. In the desert, achieving maximum density is critical to prevent the ingress of sand and water. Compaction is done in multiple passes, and the temperature of the asphalt must not drop below 120 degrees Celsius during the process. If it does, the mix loses its workability and the road's integrity is compromised. A key feature of Dubai's highways is their multi-layered structure. The base course is made of a coarse-grain asphalt. The middle, or binder course, uses the modified bitumen and acts as a shock absorber. The top, or wearing course, is a thin layer with a high polymer content to provide grip and durability. In some cases, reflective minerals are added to reduce heat absorption. In the desert, it's not just the heat. Dust, wind, and humidity changes all have an impact. Asphalt plants in Dubai are equipped with advanced air filtration systems, and the mixes themselves are tested for resistance to abrasive wear and thermal expansion. In the RTA's laboratories, every batch of asphalt is checked for viscosity, density, and thermal stability. If it fails to meet the standards, the entire batch is rejected. This journey, from oil tanker to finished highway, takes several days, but involves dozens of quality control stages. And it is because of this meticulous process that Dubai's roads can withstand the daily punishment from thousands of vehicles without melting under the desert sun. Over 1 million tons of asphalt are produced in Dubai annually, and this figure is growing with the city's infrastructure. The DXB asphalt factory alone has a capacity of 240 tons per hour, allowing it to supply major projects without interruption. For comparison, an average plant in Europe produces around 150 tons per hour. Interestingly, asphalt is the most recycled material in the USA, with over 99% of old pavement being reused. Dubai is also actively adopting recycling, especially during the reconstruction of older highways.
Right now, 160 feet beneath London, in total darkness, a steel worm the length of an aircraft carrier is crawling forward. Inside it, a factory floor with conveyor belts, a cafeteria, toilets, and 40 engineers. The machine digs the tunnel it's traveling through. It lays concrete walls behind itself. It replaces its own teeth on the move. This is a TBM, a tunnel boring machine. The head with a cutting wheel as tall as a 6-story building. Total length of the whole assembly, 1,300 feet. Weight, 10,000 tons, like the Eiffel Tower lying on its side. One of these costs more than a 5th-generation fighter jet. And if it gets jammed in the rock, they won't retrieve it. They'll abandon it. Pour concrete over it and leave it there forever. Under London alone, 8 such machines are already buried. And there's one trick that lets a TBM chew through solid rock at 33 feet per day without stopping for a single second. I'll show you that trick right at the midpoint of this video. But first, let's go inside the steel worm. From the outside, it's just a round steel wall. You only see the machine's face. A black wheel, 56 feet across, studded with steel discs. That's the cutting edge. Beyond it, into the tunnel darkness, stretches a long tail of structures, rails, hoses, and systems. This is what a modern TBM looks like, a tunnel boring machine. Not a machine in the usual sense, more like an underground factory on wheels. It has its own hydraulics, its own power plant, its own conveyor system running for miles, its own crew. Total length, up to 1,300 feet. That's 4 football fields laid end to end, hidden underground. On the front wheel, dozens of cutter discs. These are thick steel rollers made of tungsten carbide, each one the size of a large stock pot, weighing 440 pounds. Each one costs as much as a new car. There are over 60 of them. The wheel turns slowly, 1 or 2 rotations per minute. Calm, impassive. But it's precisely this unhurried pace that's chewing through granite right now. And this is where things get really strange. Cutter discs don't saw rock, they crush it. The cutter head presses its entire machine weight into the face and squeezes the discs against the rock. Each disc takes 25 tons of load. That's the weight of a city bus, forced through a 2-inch steel ring. Under that kind of pressure, granite stops being stone. It becomes brittle, like a cracker. Cracks, chips off, crumbles into pea-sized bits. The wheel shaves off about 1 inch per revolution. Per shift, 16 to 24 inches of rock turned to rubble. Inside the machine, it sounds like a constant low growl. The walls vibrate. The air smells like hot iron and stone dust. In the operator's cab, screens show pressure on each of the 60 discs individually. If one disc breaks and stops transferring pressure, the neighbors get overloaded. Within half an hour, the TBM just loses its teeth. One lost disc, and the machine's down for a day. Every hour of downtime costs 80,000 euros. But that's only one task. The rock being cut has to go somewhere. Right behind the cutting wheel sits a massive funnel, the machine's shield. Everything the wheel chews up dumps in here. Next up, the conveyor belt. A long rubber belt, about 3 feet wide, runs through the entire TBM, backward through the whole 1,300-foot train all the way to the tunnel exit. In a single shift, 5,000 tons of rock travel down this conveyor. That's 200 dump trucks packed to the brim. 200 truckloads of underground debris every 12 hours. And that's just from one machine. If the rock's dry, the conveyor coughs up dust and rumbles with stones. If there's water at the face, behind the machine flows a real underground river of liquid mud. Pumps the size of houses stand by to pump it up to the surface. If they fall behind, the TBM starts to drown. And right now, as we speak, something that should be impossible is happening. The machine is simultaneously cutting rock and moving forward, pushing itself 10 meters a day. Here's how. ATBM has no wheels, no tracks, nothing that normally moves machinery. The machine moves forward only by pushing off its own tunnel. Sounds weird, but look. Around the perimeter of the body sit hydraulic jacks, about 20 of them, each one thick as a utility pole. Together, they can push with a force of 100,000 tons. That's the weight of 17 Eiffel Towers directed at a single point. With these jacks, the machine braces against the tunnel wall behind it, against the concrete rings already installed, and pushes itself forward. 2 inches, then 4, then 8. And here's the main trick I promised at the start. While the front head chews through rock, at the exact same time, in the rear section of the machine, a massive mechanical manipulator is working, the erector, a robot arm weighing 100 tons. It doesn't wait for cutting to stop. It grabs the next concrete ring and sets it in place simultaneously. The machine never stops. Cutting happens without a break. Tunnel assembly happens without a break. It's like a train laying track beneath itself without slowing down. That's exactly why a TBM pulls off its legendary 30 feet a day. The concrete rings that make up the tunnel aren't poured on site. They're prefabricated at a massive plant on the surface. Each ring consists of 6 or 7 massive segments. Each segment weighs 6 tons. Picture a vertical concrete wall 16 inches thick and as tall as a person. These segments move forward through the TBM on a special narrow-gauge railway, heading straight to the erector. A robotic arm grabs one segment with a vacuum suction cup and places it into position. Installation precision, 1 millimeter. Any more error and neighboring segments won't fit together. A bigger mistake and the ring will crack under the pressure of earth above it. And above it, several million tons of rock are pressing down. Each installed ring is immediately compressed between 2 neighbors, the old one and the future one. The concrete doesn't work in bending, only in compression, and in that state it can hold entire mountains above its head. 40 rings like this means 130 feet of finished tunnel. Immediately, the next batch of segments will roll along them forward to the erector. Every 3 to 4 miles, the cutter discs wear down to nothing. Sharp edges turn into smooth pucks. They have to be replaced. And this is the most dangerous part of the entire TBM operation. The wheel sits at the front of the machine, underground, under massive pressure from water and soil. You can't just pop open a hatch. A ton of liquid mud under pressure will come flooding in. So they use a hyperbaric chamber. Before replacement, the air in front of the wheel gets compressed to 5 atmospheres. That's the pressure of a submarine at 150 feet. 2 workers in specialized suits enter the chamber, go through airlock procedures, and end up right at the cutting wheel. They've got 15 cutters to swap out per shift. Time limit: a few hours. If the compressor fails, pressure drops, the face collapses. If a worker slips up, a sharp-edged disc weighing 450 pounds slides off and snaps bone like a twig. After the shift, reverse airlock, an hour of decompression. Otherwise, your blood boils from the inside. It's the work of divers underground. And this whole time, the TBM has to hit exactly where it's being steered. Not an obvious task. The machine travels blind through rock. It can't see daylight. No GPS works under 650 feet of earth. Instead, laser targets. On each segment of a laid tunnel, there are reflectors. A laser theodolite constantly fires a beam at these points and calculates the machine's position within a fifth of an inch. On the control panel, the operator sees the actual trajectory and the calculated one. The slightest tilt of the head, and half a mile later, the TBM will emerge 30 feet off target. That's catastrophic. Under the English Channel, the opposing British and French TBMs drove toward each other for 30 miles in total darkness, through rock beneath the seabed. And they met with a discrepancy of 6 inches, over 30 miles. That's like firing a rifle in New York and hitting a coin in Philadelphia. Underground precision. It's not a question of quality, but a question of whether the machine makes it back to daylight or not. When the tunnel's done, the TBM reaches the finish. And here's where things get weird. Most machines never come back. They're buried. At the very end of the route, crews prepare a side niche in advance, a short, dead end. The TBM drives in. The crew removes the cutter head, the most valuable electronics, and some of the hydraulics. That stuff gets hauled to the surface. Everything else, the 300-foot-long body, the conveyor, the erector, the motors, stays in the niche forever. The crew fills the machine with concrete and walks away. The reason? Cold, hard economics. To turn around and drag a beast like that back out, you'd have to rebuild its entire route in reverse. That costs more than making a brand new TBM. Under London, 8 of these machines are already buried. Under the Bosporus, 2. In the Alps beneath the Gothard, 4. Across Europe right now, dozens of buried TBMs lie underground. Each one, a steel tomb as long as an aircraft carrier, and no one will ever see them again. Every subway station you walk through, bored by a TBM. Every rail tunnel in the Alps. Every drainage collector under a major city. London's Crossrail, 26 miles. Gotthard in Switzerland, 35. Brenner between Austria and Italy, 40 miles. The longest tunnel in human history. Without TBMs, none of this exists. A modern city isn't just what you see above ground. It's also the dark miles of infrastructure where trains run, water and sewage flow, cables race. Each of these miles is impossible to dig by hand, only with a machine the length of an aircraft carrier, with its own workshop, its own cafeteria, and its own tomb at the end of the line. And if you want to see how they make those concrete rings themselves, inside a massive open-air factory, check out the next video about tunnel segment production. Every year, over 15 billion tons of ore, coal, and rock are extracted worldwide. And hauling all of it? An army of machines you'll almost never see on regular roads. Mining dump trucks. Giants weighing over 600 tons, with wheels taller than a grown person, and a single bed that can hold several railroad cars worth of rock at once. Next to them, a regular truck looks like a toy. But the most astonishing thing isn't their size. What's astonishing is how, from simple steel sheets, bolts, and cables, emerges a machine capable of working non-stop for decades in the harshest conditions on the planet. One such dump truck can cost over $5 million and only pays for itself through relentless operation day and night. Its engine burns through up to 100 gallons of fuel per hour, and one fully loaded bed can weigh more than a Boeing 747 passenger jet. In this documentary, The Factor-In reveals how one of the most powerful transport machines in the modern world is assembled from scattered metal. The journey of a mining haul truck doesn't start at the factory. It starts at a computer. Engineers design every single part in CAD systems where the 3D model undergoes dozens of simulations for load stress, vibrations, and thermal behavior. A machine weighing over 1,300,000 pounds has to withstand the impact of falling rock, temperature swings from -40 to +120 Fahrenheit, and thousands of hours running non-stop. Every fraction of an inch of the frame, every support point, every weld seam is calculated in advance. Engineers even model how the truck will perform on steep mine inclines when fully loaded. Once the blueprints are approved, material selection begins. The main frame is built from high-strength alloy steel, capable of handling impact loads in the hundreds of tons. Suspension components go through additional heat treatment. Only when all documentation is signed off do tons of steel plate arrive at the plant. Steel sheets up to 4 inches thick arrive at the cutting shop. Here, human labor has been almost entirely replaced by automated systems. Plasma and laser cutting machines with numerical control carve out parts accurate to within a few thousandths of an inch. The plasma jet temperature hits 36,000 degrees Fahrenheit, enough to instantly slice through metal of any thickness. A modern machine can process dozens of tons of steel in a single shift, cutting hundreds of complex shapes. Even a deviation of just a few thousandths of an inch at this stage can later cause deformation in a structure weighing hundreds of tons. After cutting, parts move to bending. Massive hydraulic presses applying thousands of tons of force shape curved surfaces, stiffening ribs, and cabin elements. Metal that seemed unshakable deforms under pressure and takes the required form. Each part at this stage receives its own unique number and enters the plant's unified digital tracking system. The next stage? The welding shop. Here, thousands of individual steel components become one solid structure. The dump truck frame, capable of withstanding impacts from multi-ton chunks of rock, gets assembled on specialized jigs that lock parts in precise position. First, workers tack weld, short welds, temporary holds. Then, the robotic welding arms take over. They move with insane precision, laying down long, deep, continuous beads along massive steel components. But robots can't replace humans entirely. Not yet. In hard-to-reach spots, highly skilled welders work by hand. Every weld gets checked, ultrasound, X-ray, because a hidden crack inside the metal could later tear the whole structure apart under load. Welding the mainframe alone can take several weeks of non-stop work. This is where the skeleton of the future machine is born. After welding, the frame heads to the paint shop. The surface gets cleaned using high-speed shot blasting. Metal beads fired under pressure strip away rust, scale, and leftover weld slag. Then a layer of zinc primer gets applied, seeping into every corner and creating corrosion protection for decades to come. Only after that does the top coat go on, typically yellow, the signature color of heavy machinery visible in any weather. Meanwhile, in other shops, production of key assemblies is underway. The massive diesel engine that'll become the heart of the machine can displace over 20 gallons and pump out more than 4,000 horsepower. Just one of these engines weighs dozens of tons. Nearby, transmissions, electric generators, and hydraulic systems are being prepped. Each one is itself an incredibly complex piece of engineering, developed over years. Hydraulic cylinders that lift dump bodies weighing hundreds of tons get tested under pressure hundreds of times greater than atmospheric. Final assembly is the most spectacular stage of the entire process. In a massive assembly hall, the frame is lifted by giant overhead cranes and positioned onto assembly supports. Then, step by step, installation of components begins. The engine is lowered into the central section of the machine with millimeter precision and secured with high-strength bolts. The cooling system, fuel system, and exhaust are connected to it. Next come the electrical generators, since modern mining dump trucks operate on a diesel-electric system. The engine spins the generator, which then powers electric motors built right into the wheels. This setup allows enormous torque to be transmitted without losses through long mechanical shafts. Then the wheels are installed, each one over 13 feet tall and weighing around 5 tons. A single wheel costs as much as a premium car, and replacing one in the field requires specialized equipment and takes an entire workday. The body goes on last, a giant steel basin with a capacity exceeding 12,500 cubic feet. After full assembly, the haul truck undergoes a series of tests. Engineers fire up the engine for the first time, and its roar fills the entire shop floor. They check hydraulic system pressure, coolant temperatures, and generator operation. The machine rolls out to the test grounds where it makes its first moves, raises and lowers the empty bed, and runs through braking and maneuverability tests. Every sensor, every electrical circuit, every safety system gets checked under real-world load. Only after all parameters are confirmed does the haul truck receive its markings, go through final cleaning, and get prepped for shipment. But shipping it the usual way? Impossible. The machine gets broken down into large modules, loaded onto specialized trailers, and hauled to the job site, where the whole assembly process happens again, this time right at the mine. From digital blueprints and tons of steel sheets to a finished machine weighing over 600 tons, the entire process takes months of intense work by hundreds of engineers and workers. A mining haul truck isn't just transportation, it's the living embodiment of engineering genius, where every bolt, every weld, and every hydraulic line is calculated for decades of operation in extreme conditions. These machines rarely appear in the frame of everyday life, but they're the ones driving global mining operations, supplying raw materials to the entire global industry. Without them, modern metallurgy, energy production, and construction would be impossible to imagine. If you want to see more industrial processes like this, subscribe to the Factorin channel and stay tuned for new episodes.
Somewhere in the world right now, a concrete giant is being born, capable of spanning a space as wide as an entire basketball court, and all of this without a single support. How can a lightweight hollow slab withstand the weight of hundreds of tons? Why do builders say that within these slabs lies the power of steel muscles? And most importantly, what secret makes them so unique that annually in North America, over 17.5 million square meters of these structures are produced, the area of 30 pentagons? Stay until the end, and you'll discover the secret that will forever change your understanding of concrete. The slip former machine crawls along a 590-foot forming bed at approximately 4 feet per minute. Doesn't sound terribly fast? Now let's do the maths. That's 200 feet per hour. That's nearly the length of an Olympic swimming pool, born from concrete in less than an hour. During a single 10-hour shift, one such bed can churn out almost half a mile of perfectly formed concrete slab. Now for the main feature, the voids. These holes inside aren't simply for aesthetics. They reduce the slab's weight by nearly 50% compared to a solid slab of the same thickness. Imagine constructing an office center with a floor area of 100,000 square feet. If the floors were made from ordinary solid concrete, their weight would be approximately 5,000 tons. But with hollow core slabs, just 3,000 tons. We've just removed 2,000 tons of excess weight from the building. That's the weight of roughly 500 adult elephants, which foundations and columns no longer need to support. This allows the entire building structure to be made lighter, more elegant, and most importantly, considerably cheaper. But how can such a lightweight slab be strong? The secret lies in those tension steel muscles. The concrete used in these slabs isn't what you have on your pavement. This is high-strength concrete, withstanding pressure exceeding 8,000 pounds per square inch, whilst ordinary concrete manages only 3 or 4,000. And the steel cables inside are tensioned with such force that they create constant compression within the slab. That's precisely why these slabs are adored for constructing car parks, supermarkets, and open-plan offices. Annually in North America, over 17.5 million square meters of hollow core floor slabs are produced. This figure simply doesn't fit in one's head. It's an area sufficient to construct 30 buildings as gigantic as the Pentagon. Every year. This isn't merely a building material, it's an entire industry built on speed, efficiency, and intelligent use of resources. Everything begins not in a concrete mixer, but on a gigantic, perfectly flat aerodrome inside the workshop. This is the forming bed. Imagine a perfectly level, polished steel runway several feet wide, but in length 400, 500, and sometimes 600 feet. Beneath this runway lie pipes through which hot water or steam circulates to keep it warm. At both ends of this runway stand massive steel anchors embedded in thick concrete foundations. Between these two anchors, high-strength steel cables or strands are tensioned. This isn't ordinary wire. It's several steel threads woven together, each capable of supporting the weight of a motor car. They're laid along the entire length of the 590-foot bed, forming the future skeleton of the slab. One end of each cable is securely fixed in the anchor. To the other end is connected a gigantic hydraulic jack, and this jack begins to pull. It tensions each of these steel cables with a force of 30 or 40,000 pounds. The steel muscles tense up, becoming as hard as the strings of a gigantic guitar and store colossal energy within themselves. This is secret number 1, pre-stressing. When the steel skeleton is tensioned, the main character enters the stage, the forming machine or slip former. This is one of the most astonishing machines in the construction world. Imagine a strange, squat, self-propelled creature that slowly crawls along rails beside our long bed. At the top, it has a large hopper into which concrete is poured. But this isn't ordinary liquid concrete. This is so-called zero-slump concrete. It's so dry that it resembles damp earth. And so this machine begins its slow journey. Secondly, special vibrators and compactors with incredible force tamp this dry mixture, making it extraordinarily dense. And thirdly, most importantly, inside the machine are special forming tubes that, whilst vibrating, pass through the thickness of the concrete, leaving behind perfectly round, smooth voids. The machine, like a gigantic concrete snail, slowly crawls forward, and behind it, like a trail, remains a perfectly formed, endless concrete slab. Because the concrete is so dry, it instantly holds its shape and doesn't spread. This is secret number 2, voids that make the slab 50% lighter than a solid one. When the machine reaches the end of the 590-foot bed, its work is complete, but our slab is still green and weak. The time arrives for a spa treatment. Workers cover the entire length of this concrete ribbon with enormous insulating tarpaulins. Hot steam is fed beneath these tarpaulins. This creates a sauna effect that dramatically accelerates the chemical reaction of concrete hardening. Under normal conditions, concrete needs weeks to gain full strength. But in this hot, humid atmosphere, it reaches the required strength, over 5,000 pounds per square inch, in just 12 or 24 hours. When the concrete has hardened, the moment of release arrives. Workers slowly release the tension on the hydraulic jacks. Now it's not simply concrete, it's pre-stressed or compressed. This means that when a load acts upon it from above, attempting to bend it, it must first overcome this built-in compression force. This is precisely what allows it to span enormous distances without additional supports. And the final act of this performance? Cutting. Along rails beside our long concrete ribbon travels a gigantic saw. This is a monster with an enormous disc covered in industrial diamonds. With a deafening roar and fountain of sparks and water, this saw cuts the slab with incredible precision into pieces of the required length. Ready, perfectly level, lightweight, and incredibly strong slabs are lifted by gigantic cranes and loaded onto lorries.
Every year, the world produces over 100 million cubic meters of MDF boards. Picture this. If you laid them out as a road 30 feet wide, you could wrap it around the entire planet at the equator, and that's every single year. But few people know that these perfectly smooth panels aren't born from wood, but from trash, sawdust, scraps, and old newspapers. How does ordinary dust transform into a material that revolutionized the furniture industry? And what secret lies in a process where steam, resin, and hundreds of tons of pressure turn chaos into perfection? Stick around till the end. You'll see what's hidden behind every gleaming piece of furniture in your home. The base for MDF isn't solid logs, but what used to be considered trash: sawdust, wood chips, scraps, and even old waste paper. It's a triumph of resource efficiency. These mountains of wood waste arrive at the factory and first get thoroughly cleaned. Powerful magnets pull out any metal contaminants, nails, staples, while screening systems remove sand and stones that could damage expensive equipment. After that, the raw material goes into a huge vat where it's washed and steamed with hot steam. This isn't about cleanliness. The steam is there to soften lignin, nature's glue that holds wood fibers together. Now begins the most critical stage, the one that sets MDF apart from its rougher cousin, particle board. The prepped softened chips get fed into a machine called a defibrator or refiner. Picture two giant metal discs, like millstones, spinning toward each other at incredible speed. Their surfaces are covered with an intricate pattern of sharp ridges and grooves. The wood pulp gets caught between these discs, and they literally comb it apart into its tiniest components, tearing it into individual wood fibers. This isn't chips anymore. It's something like fluffy, damp cotton or wood flour. We've just deconstructed wood down to its basic building blocks. Next, this fibrous mass needs to be dried, but it has to happen fast, before the fibers start clumping together, so they get blown into a long, hot drying tube. A stream of hot air catches the fibers, and as they fly through this tube, all excess moisture evaporates out of them. And right here, while the fibers are still hot and swirling in this vortex, the next critical stage happens: resin application. A fine mist of binding agent gets sprayed into the airstream through special nozzles. This is urea formaldehyde resin, our glue. This mist coats every tiny fiber, covering it with a thin, sticky film. It's an incredibly efficient method, guaranteeing perfectly even glue distribution. Interesting fact, urea formaldehyde resin was first synthesized in the 1920s, but it only started being used on a massive scale in wood panel production after World War II. Now this resin-saturated, dry, and fluffy light mass is ready to become a board. It goes into the forming machine. The stream of fibers settles onto a wide moving conveyor belt, forming a thick, loose, and perfectly even mat. Special rollers compress it slightly, and giant knives cut it into pieces of the required length. It already looks like the future board, but for now, it's just a thick, soft mattress of wood fluff. And then comes the climax, hot pressing. This loose mat rolls into a giant press. It might be either a multi-story press that simultaneously compresses an entire stack of boards, or a continuous press that looks like giant caterpillar tracks. And here, two powerful forces act on our mat at once. First, colossal pressure. The press plates squeeze our loose mattress with a force of hundreds of tons, reducing its thickness several times over and forcing out all the air. The wood fibers squeeze together tightly, creating an incredibly dense structure. Second, high temperature, 400 degrees Fahrenheit. This heat does two things. It activates the resin, causing it to polymerize and bond the fibers into a single monolith, and simultaneously evaporates any remaining moisture, which escapes from the board as hissing steam. After just a few minutes in this steel embrace, the loose mat transforms into a solid, dense, perfectly flat, and still very hot MDF board. Pressure in modern presses can reach 700 pounds per square inch. Imagine an adult cow standing on an area the size of a postage stamp. After pressing, the hot boards can't just be stacked. They need to cool down to relieve internal stresses. They're placed in a special fan cooler that looks like a giant card catalog, where they slowly cool down, fanned by air. Once the sheets have cooled, it's time to give them that finished look. First, they're stacked in tall piles and left to rest for a few days. This stabilizes their internal structure. Then each sheet runs through a sanding machine. Picture a giant belt sander with multiple heads. Wide abrasive belts strip away a thin surface layer from both sides, bringing the sheet to a perfectly precise thickness, say 16 or 18 millimeters, and creating that famous paper-smooth surface. And the final touch? Cutting. Massive saws slice the large production sheets into standard commercial formats. After that, every batch goes through strict quality control. Density, strength, thickness, and surface quality all get checked. Modern MDF panels have a density of 37 to 50 pounds per cubic foot. That's 1.5 times denser than natural pine. The finished, perfectly smooth panels get labeled, packed up, and shipped off to furniture factories, where they'll become the foundation for elegant and stylish pieces in our homes, silently demonstrating what a noble journey ordinary wood dust can take. The global MDF market? It's a giant machine churning out more than $25 billion a year. And this machine isn't planning to stop. Forecasts say it'll grow 6% annually. That means demand for this smooth material is absolutely insane. So, who's the head chef in this kitchen? The undisputed king, China. They produce over 50% of all the MDF in the world. Chinese factories run around the clock, turning out millions of cubic meters of boards for domestic use and export. But Europe's no slouch either, with powerhouses like Germany, Poland, and Turkey cranking out millions of cubic meters of high-quality board. German manufacturers are especially famous for innovative technology and strict environmental controls. Now let's talk volume. Every year, the world produces about 100 million cubic meters of MDF. That number is so massive, it's impossible to picture. Let's try anyway. Imagine a road. If you took all that MDF and laid it out as a road 30 feet wide and 10 inches thick, you could wrap a belt around the entire planet at the equator. Generously, an endless stream of material transformed into furniture, doors, and panels for our homes. What's fascinating is that MDF has unique properties you won't find in natural wood. No knots, no cracks, no voids. You can mill it, creating complex decorative elements that would be impossible or way too expensive with solid wood. That's exactly why MDF became the #1 material for kitchen cabinet doors, raised panel doors, and decorative trim. Plus, MDF holds fasteners incredibly well. Screws grip far more securely than in standard particle board. And that smooth surface? Perfect for paint. It goes on evenly, no fuzz, no grain, creating a finish that looks like plastic or even glass.
Environmentalists often criticize MDF for using formaldehyde resins, but modern technology allows manufacturers to produce E0 and E-half grade boards, where formaldehyde emissions are lower than in natural wood. And so, having journeyed from a pile of sawdust and scraps through a steam bath, defibrator, pressing under hundreds of tons of pressure, and final sanding, this amazing material emerges. Dense, strong, perfectly smooth, and ready to become part of our homes. From humble kitchen cabinets to luxurious carved facades, from simple interior doors to intricate decorative panels, MDF works everywhere, the silent hero of modern interiors. It doesn't demand admiration, doesn't seek glory, but it's what makes our homes cozy and beautiful. And now you know its story, from trash to treasure, from wood dust to a masterpiece of engineering.
What if one of the most common metals on Earth has a hidden property that even some engineers still underestimate? A metal that boils like water and vanishes into thin air during production, then gets reborn as gleaming ingots. We see it every day, but almost no one knows what the underground cities where it's mined look like, or what giant machines make the ore flare up like tiny controlled earthquakes. Zinc, the fourth most consumed metal in the world after iron, aluminum, and copper. 12 to 13 million tons of zinc are produced every year. 60% of all zinc goes into galvanizing steel. Without it, bridges, cars, and buildings would rust many times faster. But here's the shocker. At 2700 degrees Fahrenheit, zinc literally turns into vapor and disappears into the air, and then condenses back into liquid metal. In this video, you'll learn things you never suspected, and at the end, the main secret will be revealed that will forever change how you think about zinc.
Picture a massive underground mine somewhere in China, Australia, or Peru, the world's biggest zinc producers. These are entire underground cities stretching hundreds of feet, sometimes even miles beneath the Earth's surface. We're not talking about simple holes in the ground. This is a network of tunnels, shafts, ventilation systems, and lift shafts. Powerful drilling rigs bore holes into the rock, blast holes. Explosives get packed into these holes. After a carefully controlled blast, massive volumes of rock break apart. It's like a spectacular but controlled earthquake in miniature. Dusty air gets quickly cleared by powerful ventilation systems, which also pump fresh air down to these depths. The broken ore then gets loaded onto massive underground trucks or conveyor belts using front-end loaders. It's a genuine underground transportation flow, continuously moving, hauling tons of ore to the central lift shafts. From there, the ore rises to the surface using powerful elevators or specialized conveyor systems, climbing hundreds of feet straight up.
At every stage, from drilling to hoisting, strict safety protocols are followed because working underground demands maximum caution. Once the ore reaches the surface, it still looks like ordinary rock, containing only a small percentage of zinc. To extract the valuable mineral, the ore goes through a concentrator plant, a whole complex of sophisticated processes. The first step is crushing and grinding. Massive chunks of ore into crushers that, with a deafening roar, break them down into smaller pieces. Then this crushed ore moves into ball or rod mills, giant rotating drums filled with steel balls or rods. Inside these mills, the ore is ground down to an extremely fine powder, almost like flour. This is critically important to free the zinc mineral crystals from the surrounding rock. The next key stage is flotation. The ground ore powder is mixed with water and special chemical reagents in large tanks called flotation cells. These reagents selectively stick to the zinc mineral particles, making them water repellent. Then air is pumped through this mixture, creating millions of tiny bubbles. The zinc mineral particles latch onto these bubbles and rise to the surface, forming foam. Other unwanted minerals stay at the bottom. This enriched foam is collected. That's your zinc concentrate, which can contain up to 60% zinc. Since zinc is often found alongside lead, the processing plant may run multiple flotation cycles to separately extract zinc concentrate from lead concentrate. The zinc concentrate you end up with still isn't pure metal. It has to go through metallurgical processing to get metallic zinc. And now we enter the world of extreme temperatures. If the pyrometallurgical method is used, the zinc concentrate first undergoes roasting. The concentrate is heated in specialized furnaces at temperatures around 1800 degrees Fahrenheit. This removes the sulfur, which is part of the sulfide ore, converting it into zinc oxide. The sulfur transforms into sulfur dioxide gas, which is captured and used to produce sulfuric acid, a crucial industrial product. This not only cuts down on air pollution, but also creates an additional valuable product. Next, the zinc oxide is mixed with coal and heated to even higher temperatures, over 2200 degrees Fahrenheit, sometimes even 2700 degrees, depending on the specific furnace technology. At these extreme temperatures, a reduction process occurs. The carbon strips oxygen away from the zinc oxide, freeing up pure metallic zinc. And this is where that incredible wow moment of vaporization happens. At these temperatures, the metallic zinc transitions into a gaseous state. It evaporates. Zinc has a relatively low boiling point compared to other metals. So in these furnaces, where the temperature is significantly higher, zinc literally turns into vapor, which rises and gets collected in specialized condensers. The vapor cools and condenses, turning back into liquid metallic zinc. This liquid zinc is then poured into molds to create ingots or granules. Now for the history. Zinc has been known to humanity for thousands of years, though it was only isolated as a distinct metal in the 16th century. Ancient civilizations used brass, an alloy of copper and zinc, without knowing it actually contains zinc. In India and China, people learned to smelt zinc as far back as the Middle Ages. But modern industrial zinc production only began in the 19th century with advances in smelting technology. The primary use of zinc: galvanizing steel. Around 60% of all zinc produced goes toward protecting steel from corrosion. Zinc coating on steel creates a sacrificial layer. The zinc oxidizes instead of the iron, protecting the structure. Without zinc coating, the lifespan of steel products would drop dramatically, leading to massive economic losses and a surge in resource demand. 15 to 20% of zinc goes into making alloys like brass and die casting alloys. These alloys end up in car parts, home appliances, toys, plumbing, and electronics. Another 10 to 15% becomes zinc oxide and other chemical compounds. Zinc oxide has crazy wide applications: sunscreens and cosmetics, paints, ceramics, rubber manufacturing, and even livestock feed supplements. Its antibacterial and protective properties make it a universal ingredient. The rest of the zinc gets used in batteries, as a micronutrient in agriculture to boost crop yields, and in pharmaceuticals and dietary supplements, because zinc is absolutely vital for the human immune system. As for prices, like most commodities, zinc prices swing with global supply and demand, economic cycles, and what's happening in the biggest producer and consumer countries. Yet demand for zinc remains steady or growing, driven by urbanization, infrastructure development, and the need to protect metals from corrosion worldwide. This makes zinc a crucial indicator of global economic health. Zinc ranks as the fourth most consumed metal on the planet, after iron, aluminum, and copper. That alone tells you just how massive its importance is for the global economy and industry. Annual worldwide zinc production sits at roughly 12 to 13 million metric tons. These are enormous volumes, underscoring its irreplaceability across hundreds of applications. The primary zinc mining regions are China, Australia, and Peru. These three countries together account for a significant share of global zinc ore extraction, making them key players in the market. For instance, China isn't just the largest producer, it's also the world's biggest zinc consumer, reflecting its powerful industrial expansion. Other major producers include India, the United States, Mexico, and Canada. When it comes to reserves, the U.S. Geological Survey estimates global zinc reserves at roughly 250 million metric tons. On top of that, there are what's called resource spaces, potential deposits that haven't been explored yet or aren't economically viable to mine right now. Those are estimated at over 1,800 million tons. These numbers show that zinc, unlike some rare metals, will last for many decades, even with growing consumption. Most zinc is mined from underground operations, entire subterranean cities stretching hundreds of feet, sometimes several miles beneath the Earth's surface. These aren't just holes in the ground, they're networks of tunnels, shafts, ventilation systems, and hoisting shafts. It all starts with exploration. Geologists, like detectives, hunt for ore bodies, sections of rock where the concentration of zinc, which, by the way, usually occurs as sulfide ore, like sphalerite, and almost always comes with lead, silver, and sometimes copper, is high enough to make it worthwhile. Once a deposit is discovered, mine construction begins. This involves sinking vertical shafts, which provide access to the ore, lift materials up, lower equipment down, and creating horizontal tunnels, or drifts, that lead directly to the ore veins. The actual ore extraction process? Dynamic, risky. Miners use specialized equipment, powerful drilling rigs that bore holes into the rock, called blast holes. Explosives get packed into these holes. After a carefully controlled detonation, massive volumes of rock shatter. It's like a spectacular earthquake, in miniature, under control. And that's how, starting from an underground explosion, through crushing into powder, through flotation with millions of tiny bubbles, through roasting at 1800 degrees and reduction at 2700 degrees, where the metal literally turns into vapor and vanishes into thin air, then condenses back into liquid zinc, a metal is born that shields steel from rust, makes bridges possible, cars, skyscrapers, without which the modern world would look completely different.
This ship doesn't go around the ice, it goes straight through it. 10 feet of frozen ocean, and it doesn't care. I'm standing in a shipyard where they're assembling the hull of a nuclear-powered icebreaker, and in front of me is a giant steel skeleton that will soon be working where temperatures drop below -50, and ice pressure can crush any ordinary structure like a tin can. You know, I usually go look at things you can touch without risking your cheek freezing to them. But today, I slightly overestimated my ambitions. And right now, I'm going to show you how a machine is born that makes even the Arctic itself back down. The first thing that hits you at the shipyard isn't the size, though the future vessel stretches over 500 feet long, and individual hull plates run several inches thick. What stuns you is the steel itself. They don't use ordinary rolled stock here. An icebreaker hull demands special steel grades that stay flexible even in brutal cold. Regular steel turns brittle in the freeze. Strike it, and it'll crack like glass. This stuff, though, has to take impacts from ice fields and not fail. The engineers explain it simply. The hull needs to give a little, flex slightly under pressure. Otherwise, the Arctic will just snap it. Massive steel plates arrive at the yard already rough processed from the rolling mill. Each plate weighs dozens of tons, and when the crane lifts one into the air, it looks like a chunk of an apartment building somebody randomly decided to relocate. But the icebreaker's shape doesn't appear all at once. First, these plates pass through giant rollers that slowly, with enormous force, bend them to the required angle, giving the metal that crucial curve without which the hull can't push ice aside. In front of me, steel rollers, each as thick as a decent tree trunk, stacked one above the other. Between them, they slowly feed a flat steel sheet. Heavy, rigid, seemingly completely inflexible at first glance. The operator gives the command, and the mechanism starts moving. The rollers rotate at low speed, but with massive force. The sheet gradually gets pulled inside, and at some point, you can see it start to change shape. First, it's a barely noticeable bend. Then the radius increases, and the metal's no longer flat. It curves smoothly, as if obeying someone's will. The sound here is unique, a muffled pressure, grinding, and a slight crackling, like the metal reluctantly gives in. I'm standing nearby, and I hear how the steel literally groans under the load, a sound like you're pressing on something really stubborn, and it's grudgingly surrendering. They might roll the sheet several times, adjusting the roller positions each time, until they get the exact angle or curvature. And there in front of you is no longer just a piece of steel, but part of a future hull that perfectly matches its contours. By the way, if you're into stories about how seriously complex and powerful machines are built, hit subscribe so you don't miss the next episode. Now, let's keep going. Next comes the assembly of sections, and this looks like a giant construction set, except each block weighs as much as a small locomotive. Individual hull blocks are assembled in the shop. These can be sections 60 or even 100 feet long. Inside each block, there are already bulkheads, cable routes, and even foundations for future decks. In other words, the hull isn't built from scratch in one spot. It's assembled in pieces, like a puzzle, just really heavy and really hot to produce. I walk into the shop and there are finished sections already standing there. These aren't just sheets of metal, they're entire fragments of the future ship. Inside each one, you can see passageways, openings for cables, spots where pipes, wires, and entire life support systems will run later. Then these blocks are transported to the slipway and joined together. The cranes move in. They lift the section into the air slowly, smoothly, no sudden movements, and transport it to the slipway. There, they carefully lower it and fit it against the already installed parts of the hull. At this moment, you literally see separate pieces starting to come together as one. The future icebreaker takes shape right before your eyes. Welding is a whole different story. You can't just run a bead and go grab coffee. Every joint goes through multiple levels of inspection. First, the welder lays the main seam. Then they check it with ultrasound to make sure there are no voids or cracks inside. If something's off, they cut it out and do it over. I watched them redo one seam 3 times, and nobody even got stressed. That's standard practice here, because the price of a mistake in the Arctic isn't just a breakdown, it's a potential catastrophe. And that's how it goes. Every seam, every joint, along the entire length of the hull. We should talk about the hull shape. An icebreaker doesn't just have a strong bow, it's specifically designed to climb up onto the ice and break it with its own weight. That's why the bow section has that distinctive slope, and they reinforce it with extra layers of steel. In some spots, the thickness multiplies several times over, and inside they add ribs that distribute the load along the entire length of the ship. While I'm walking around here, there's constant movement everywhere. Cranes, platforms, people in hard hats, for whom all this is just another workday. Though honestly, when they're moving a whole section weighing dozens of tons right over your head, you kind of rethink the word ordinary. One of the engineers jokes that the scariest thing here isn't the cold or the metal, it's when someone forgets their lunch in the shop, because finding it among all this scale is practically impossible. When all the sections are connected, the hull starts taking its final shape. Its length becomes physically tangible. You walk alongside and catch yourself thinking it's like strolling past an apartment building, only horizontal. The height of the hull is impressive too. Several levels that will eventually become decks, engine rooms, and crew quarters. After that comes surface treatment. The metal gets cleaned, anti-corrosion coatings applied, painted with special compounds that reduce water friction and protect the hull from salt and ice. It looks like cosmetics for a giant, but in reality, this coating determines how many years the ship can operate without major repairs. And that's not an exaggeration. Arctic saltwater and constant ice friction can destroy unprotected metal in just a few seasons. Modern nuclear icebreakers can ram through ice up to 9 feet thick while underway, and the newest designs are rated for ice up to nearly 15 feet thick. Power, that's a whole other story. Heavy icebreakers can pump out over 75,000 horsepower, and without that, they simply wouldn't budge the ice. I'm standing here staring at this hull, and it hits me. This isn't a finished vessel yet. There's no reactor in here, no propellers, no control systems. But even now, the main thing is crystal clear. This is a structure built to battle the elements, where every millimeter of steel serves a purpose. And when she heads out to sea, she won't just sail. She'll carve a path where other ships wouldn't even dare to go. I'm gonna stick around here a bit longer. Listen to that metal grinding. Watch these machines come to life. Then head out to prep your next adventure. Because after something like this, you want to find something just as massive, just as complex, just as beautifully insane. When you stand next to a structure like this, you start seeing what humans can actually build differently. Not on a computer, not in theory, but right here, with hands, steel, and fire. And I think I've already got a couple ideas where to head next. So stick around, it's gonna be good.
Every hour across the globe, dozens of nuclear reactions, but only a handful know that at the heart of every atomic bomb lies a material capable of destroying a city in seconds. This isn't just a weapon, it's a miniature star, crafted by human hands. You'll discover how ordinary uranium births an explosion with the force of 1,000 suns, why sand in New Mexico turned to glass, and what happened to an island that no longer exists. And most importantly, what secret hides inside a nuclear warhead. Watch until the end, because the finale will change how you see the modern world. Back in the day, when the world was just learning to hear the voice of the atom, a few curious minds peered inside the invisible, into the heart of matter. Those were the years when science was feeling its way forward, but with great determination. German chemist Otto Hahn, along with Fritz Strassmann, like alchemists of a new world, discovered that uranium could split. It was as if ice cracked on a river, behind which a giant lay sleeping. While Europe prepared for war, a group of people secretly gathered across the ocean, later to be called the Masters of Atomic Fire. In the New Mexico desert, the Manhattan Project began. Ordinary physicists, Oppenheimer, Fermi, Teller, became the creators of the greatest force humanity had ever seen. In the summer of 1945, beneath the clouds of dawn, the first nuclear bomb exploded. Sand turned to glass, sky to fire. And in the absolute silence, one scientist whispered, "Now I am become death, the destroyer of worlds."
But the story didn't end there. Days later, Hiroshima and Nagasaki became pages of grief. And just when the world thought it had seen everything, the USSR answered. Under Igor Kurchatov's leadership in 1949, the first Soviet atomic bomb detonated. A decade later, the Tsar Bomba. Its power could level a city the size of Paris. History's irony. Nuclear weapons became not a sword, but a shield. Their existence forced enemies to talk. Ideas of security, control, diplomacy became more important than warfare. For the first time, humanity faced massive questions. Can we negotiate so everyone survives? That's how deterrence doctrine was born. Don't attack, because you know attacking means catastrophe. And while this balance is far from perfect, it's delivered decades without global war between superpowers. An entire era. Cold, anxious, but without mass battlefronts.
Nuclear research sparked whole new industries: nuclear power, reactors on submarines, medical diagnostics. Even space projects got a boost from understanding the atom. To create the most terrifying thing, we learned to grasp the most complex. Yes, nuclear weapons are dangerous, but they're also a mirror of human wisdom. We built something incredibly powerful and chose not to use it on a massive scale. This is a story about power we decided to restrain, about science that taught us not to dominate, but to coexist. Deep in laboratories, where lamplight dimly illuminates blueprints, the path to building a nuclear bomb begins. This isn't just assembling metal, it's modern-day alchemy, where every gram of material holds the power of 1,000 suns. It all starts with uranium or plutonium, isotopes capable of sustaining a chain reaction.
But natural uranium is mostly uranium-238, which won't work, so they enrich it, separating out the 235 isotope using centrifuges, where gaseous uranium spins at insane speeds. Plutonium is artificial. It's produced in nuclear reactors, where uranium absorbs neutrons and transforms into plutonium, the stuff you need for a nuclear bomb. The appearance of a nuclear bomb often resembles a classic aircraft bomb, a streamlined metal casing engineered for stable descent from high altitude. In a massive hangar where the walls ring with the echo of metal, the air smells of hot steel and oil. Here begins the birth of the shell that must contain the heart of an atomic explosion. From the glowing throat of an industrial furnace flows a stream of metal, special steel, reinforced with nickel, chromium, and manganese. Its temperature exceeds 1,000 degrees. Summer sunlight looks pale compared to this fire.
Masters in protective suits with transparent face shields watch the forming process. Steel sheets bend into streamlined shapes under presses exerting hundreds of tons of force. Before their eyes, an elongated body takes shape, resembling a water droplet frozen under the pressure of the heavens. Next, mechanical arms mill the internal partitions, cut openings for tail stabilizers and locking mechanisms. Every fraction of an inch, the result of meticulous calculation, because balance during descent depends on it. After this, the casing undergoes a strengthening ritual: immersion in an anti-corrosion bath, treatment with polymer coating, application of matte paint. The color? Dark green, like a military shadow in the twilight of pine trees. And finally, testing. They drop it from height, strike it with hammers, spin it in a wind tunnel. Only after passing all trials is the casing ready to receive its lethal payload. A quiet lab, half light, a faint smell of ozone, something heavy hangs in the air. In front of you lies an open nuclear bomb, its metal casing removed, its insides, like an organism, laid bare. There's nothing extra here, no shine, no decoration, just function, just explosion. At the center, a smooth, perfect sphere. It looks like a dull meteorite. This is the nuclear core. Plutonium-239, cold and deadly, or uranium-235, heavy as a planet in your palm. Its shape, mathematical perfection, polished down to microns. Around the sphere, an entire symphony of pressure. Composite explosives, layer upon layer, like a flower turned inside out. Their job isn't simply to detonate, but to force the explosion inward. Like hands clenching to the limit, these explosive lenses must create implosion, uniform, merciless compression that drives the material supercritical. If even 1 second lags, the whole contraption becomes a heap of meaningless metal. And at the very heart of this implosion orchestra, the initiator, a tiny device waiting for its moment to release the first neutrons. Polonium and beryllium interact, creating a minuscule storm capable of triggering the irreversible. That's where the chain reaction begins, a match to an atomic forest. Then, the tamper layer. Heavy as a shadow, it wraps the bomb's core not for protection, but for containment. Uranium-238 or tungsten, not active, but absolutely critical. Their job? Delay the neutrons, force them back like an echo in a cave. Everything depends on this. The duration of the blast, its power, its climax. In the tail section, the brain. Automation, electronics, wires and sensors. Barometers waiting for altitude, radars tracking the ground, batteries sleeping, ready to wake. This is where it's all decided, when everything happens, above the city, in the air, after the drop. Without this nervous system, the blast would be an accident. But here, it's a calculation. If you look at the entire structure in cross-section, it resembles the layers of a planet, like chapters in an encyclopedia of force. The outer shell, smooth and cold. The explosive layer, mathematically arranged. The tamper, an invisible guardian. The core, like a seed of what's to come. And at the very center, a spark, sleeping until awakened. Over 62 years, the world witnessed 2,065 nuclear explosions. 5,224, that's not the number of nuclear explosions, but an approximate estimate of the entire U.S. arsenal, including active, reserve, and decommissioned warheads. Now, the number of nuclear tests that the United States conducted from 1945 to 1992 totals 1,154 detonations. Each one is a separate page in the history of power, fear, and science. The first blast, Trinity, July 16, 1945, in the New Mexico desert. It was the beginning of an era when atomic energy became a weapon. Then came Hiroshima and Nagasaki, the only instances of nuclear weapons used in combat. In the decades that followed, the U.S. tested bombs at Enuatak and Bikini atolls, in Nevada, underground, in the atmosphere, over water. The blasts had different purposes: testing new designs, demonstrating power, studying effects on equipment and living organisms. Yield varied, from from a few kilotons to 15 megatons, like in the Castle Bravo test of 1954. In 1952, the U.S. conducted its first thermonuclear test, Ivy Mike. This wasn't just a bomb anymore, but a miniature star created by humans. The explosion wiped out an entire island. In the 1960s, testing became routine. The U.S. tested warheads for missiles, aerial bombs, even neutron charges that had minimal blast waves but maximum radiation. The last official detonation happened on September 23, 1992, after which the U.S. declared a moratorium, but the arsenal remained. It gets modernized, adapted, stored. Some warheads are on submarines, some on strategic bombers, some in NATO storage facilities. These explosions aren't just technical events. This is a story about how humanity learned to control the energy of stars and put it in the service of fear. But it's also a reminder that the power capable of destroying civilization sits under the control of those who understand the price of using it. And as long as this balance holds, the world continues to exist on the edge of the abyss, but doesn't fall in.
Each year, humanity produces over 400 million tons of plastic, of which 23 million tons end up in the oceans, forming gigantic rubbish islands the size of entire countries. Consider the Great Pacific Garbage Patch alone, which covers an area 3 times that of France. Just imagine, this isn't merely rubbish, but a threat that kills millions of marine creatures annually. And by the year 2060, the oceans will be drowning in 141 million tons of plastic. But would you believe that this blot doesn't actually exist in the form we imagine it? It's an invisible trap concealing a secret. How an ordinary teenager invented a method to clean the oceans without engines, using only the forces of nature? And if you watch to the end, you'll discover revolutionary robots sorting rubbish faster than lightning, and the Interceptor, which blocks plastic in rivers using solar power. A secret that will forever change your perception of the planet's future. The waste management sector is undergoing a technological revolution thanks to the introduction of artificial intelligence and robotics. At modern waste processing facilities, robotic arms controlled by sophisticated algorithms sort refuse at remarkable speed and with exceptional precision. Computer vision systems identify different types of materials, enabling a significant increase in recycling rates. Along a wide conveyor belt moves a continuous, chaotic stream of what we've discarded: plastic bottles, crushed cardboard boxes, aluminum cans. To the human eye, it's simply rubbish, whilst for workers it represents arduous and hazardous labor. And there, above this flow, rather like a relentless predator, it hovers, the sorting robot. This isn't a humanoid android from science fiction films, but rather a high-tech industrial manipulator resembling a giant steel arm. Yet all its magic lies within. Its eyes aren't merely cameras, but complex multispectral sensors that perceive the world quite differently from us. They can distinguish materials by how they reflect light and analyze their chemical structure in fractions of a second. The heart and brain of the system is artificial intelligence. Before being deployed on the job, this AI underwent intensive training. It was shown millions of images of various types of waste until it learned to recognize them flawlessly. In this way, the robot learned to identify PET plastic, from which drinks bottles are made, denser plastic for canisters, paper, cardboard, various types of metals, and glass. And so the action begins. The conveyor belt races onwards. The camera scans the flow continuously. Artificial intelligence analyzes the image in real time. Target identified, aluminum can, it sends the signal. And a steel manipulator makes a lightning-fast, almost imperceptible lunge. A pneumatic suction cup or mechanical gripper gently but firmly seizes the can, and with a precise movement, drops it into the appropriate container. Before the can has even landed, the robot's eye has already spotted a water bottle, and the arm flies towards the new target once more. Speed? A human cannot compare with it. Some models are capable of making 100 manipulations per minute. That's more than 1 grab per second. Accuracy? The robot doesn't tire and doesn't get distracted. Its sorting efficiency reaches more than 95%, which significantly improves the quality of recyclables. This isn't simply a replacement for manual labor. It's a qualitative leap, which transforms the problem of rubbish into a genuine resource. The sorted materials, heaps of rigid plastic, cumbersome metal structures, wooden pallets, lie in separate mountains. They've already been sorted, but they're still far too large. It's here that the real heavyweight of the recycling industry enters the arena, a machine whose work is controlled, brutal force. This is the hammer mill. Outwardly, it resembles an enormous steel box, but its heart is a massive, heavy rotor, studded with rows of exceptionally robust, hardened steel teeth or hammers. Its task is simple, yet critically important: to shred. When material is fed into its vast maw via conveyor, be it an old car bumper or an entire pile of plastic drums, a spectacle of unstoppable power begins. As it rotates, the rotor's teeth seize hold of objects, dragging them inwards, and with a deafening roar and grinding, tears them to pieces. Rigid plastic cracks, metal bends and rips, wood transforms into splinters. This process is a demonstration of pure physical force. But what purpose does this destruction serve? It isn't senseless obliteration, but rather a crucial preparatory stage. Firstly, the shredded materials become uniform in size, which makes them far more convenient for transport and subsequent processing. Secondly, it's a process of liberation. The shredder breaks down complex objects into simpler components, facilitating the separation of different materials from one another. And most importantly, it creates ideal feedstock for further recycling. A heap of small plastic fragments melts far more readily in a granulator than intact bumpers. Vast accumulations of plastic in the world's oceans, such as the Great Pacific Garbage Patch, represent one of the most pressing environmental concerns. Incidentally, do you believe this patch doesn't exist? Nevertheless, through bold engineering solutions, hope emerges for cleansing our marine spaces. The problem is so enormous it appears insoluble. How does one remove something the size of several countries? Most simply threw up their hands, but not Dutch teenager Boyan Slat. In his mind was born a daring yet brilliantly simple idea, which grew into one of the most ambitious environmental projects of our time: the ocean cleanup. The project's principle is not to chase the plastic, but rather to make the ocean itself deliver the rubbish into the trap. For this purpose, giant U-shaped barriers were created. The most intriguing aspect is how this system moves. It has no engines. It drifts passively, caught by the same forces that carry the plastic: wind, waves, and ocean currents. But owing to its design, the system moves slightly faster than the plastic. This creates a small but constant difference in speed. The barrier, rather like a giant shepherd, slowly but inexorably gathers its plastic flock within its U-shaped arc. The path to success wasn't straightforward. Early prototypes fractured under the onslaught of ocean storms, but after a series of trials and errors, the system began working effectively. Now, from time to time, specialized vessels approach the laden barrier and offload the collected tons of plastic. This plastic, from old fishing nets to minute fragments, is brought ashore, where it's sorted and sent for recycling, closing the loop. Realizing that cleaning the ocean without stopping the flow of rubbish is rather like bailing water from a leaking boat, the ocean cleanup team asked themselves a logical question: couldn't one simply plug the leak? After all, research shows that the overwhelming majority of plastic enters the ocean through only a small number of the world's most polluted rivers. Thus was born the Interceptor, a technology designed to tackle the problem at its source. It resembles an elegant, futuristic catamaran, anchored mid-river. It is entirely autonomous and runs 100% on solar power, courtesy of the panels covering its upper portion. Its design has been thought through to the smallest detail, so as to be maximally effective whilst not interfering with shipping.
Every year, shipyards launch massive icebreakers and cruise liners, vessels weighing tens of thousands of tons, capable of operating for months in the planet's harshest seas. But few realize their engines are no longer inside the hull. Engineers took a radical step. They moved a power plant generating over 22 megawatts, that's more than 30,000 horsepower, and dropped it directly beneath the ship's bottom in a sealed steel pod weighing 320 tons. That's the weight of 2 fully loaded Boeing 747s. Inside that pod, a rotor misalignment by a fraction of a millimeter can shred bearings and destroy the entire drive system in just days. Watch this video to the end, and you'll discover how this underwater power plant is built, what installation mistake gets permanently hidden beneath the waves, and why this invisible enemy can obliterate a ship weighing thousands of tons in a matter of days. At first glance, it looks like a massive metal tail bolted to the ship's bottom. But inside, a full-blown electric motor. They don't mount it in the engine room like they did for decades. Here, it's the opposite. They drop the motor straight into the water, seal it tight in a steel shell, and make it work right there in the ocean. For years, no repairs, under constant seawater pressure. That's exactly why this thing's treated almost like a submarine. The idea of moving the engine outside the hull showed up relatively recently, even though engineers had been thinking about it for decades. Back in the mid-20th century, shipbuilders were trying to ditch the long shafts, gearboxes, and complex mechanical drives that ate up massive space inside the ship and bled power at every connection. The real breakthrough came in the late 1980s when Finnish engineers working on icebreakers for northern seas proposed a radical solution: move the electric motor directly into the rotating pod under the hull. If engineering stories like this grab you the way they grab me, subscribe to the channel right now so you don't miss the next episode. Hit that bell and every new video will show up for you immediately. The work was carried out by specialists from a shipbuilding company looking for a way to make vessels more maneuverable in ice. The first experiments looked risky. The engine had to be completely isolated from seawater and made to run for years without any access to it. In 1990, the first working units appeared, and just a few years later, the technology began being installed on actual icebreakers. It turned out that this design didn't just work. It worked better than any traditional setup. When it became clear that the azimuth thruster allowed a ship to move in practically any direction without turning the hull, the system was quickly adopted by cruise liner builders. This thruster can rotate 360 degrees, making conventional stern rudders and separate bow thrusters simply unnecessary. Maneuverability increases so much that a huge liner can pull up to a dock nearly sideways without tugboat assistance. Since then, this design has gradually changed the very concept of where a ship's heart should be. Not inside it, but right beneath it. I walk past hull sections that were still separate steel plates just hours ago, each one several inches thick and weighing several tons. These are already curved metal sheets, pre-rolled, so the future capsule has a smooth, streamlined shape with no abrupt transitions. No right angles here, no unnecessary joints. The form is dictated by water, not manufacturing convenience. Overhead cranes slowly lift these elements and bring them together like assembling an underwater projectile. Between the parts, they leave a narrow gap where the weld seam will go. During welding, sparks fly everywhere, and the metal glows orange. Workers move slowly, passing over every inch of the joint multiple times. No rushing, no wasted motion. First comes the inner seam, then the outer. And after that, the surface gets carefully ground down so there's not a single protrusion left to create extra drag in the water. When the hull finally closes up, it already looks like a smooth steel torpedo. Tight, solid, without a single flaw on the outside. After that, the inspection begins. Welds are scanned with ultrasound and X-rays searching for even the tiniest pores inside the metal. Any suspicious section gets cut out and re-welded, no compromises. Then they seal the capsule and pressurize it far beyond what it'll face underwater in actual conditions. If there's a weak spot anywhere, it'll show up immediately. Only after passing all tests is the hull declared ready to withstand years of service in cold seawater and constant ice impacts. Once the steel capsule is fully welded and tested, the moment arrives in the shop that the entire hull was essentially built for. They need to install the electric motor, the main power source for the future vessel. And this is where you realize just how massive everything is in marine engineering. Before installation, the motor sits on a special platform looking more like part of a power plant than ship machinery. Its diameter, nearly 10 feet, and its weight is such that regular lifting equipment isn't even considered an option. Only heavy overhead cranes work here, with every movement pre-calculated and coordinated. The rotor, the spinning part of the engine, gets lifted separately. It's a massive metal ring with copper conductors that weighs more than a fully loaded semi-truck. The crane starts moving so slowly it's almost invisible to the eye. The operator works on commands from several engineers stationed around the housing, constantly monitoring the component's position. There's no room for sudden movement and no room for error. Even a shift of a fraction of a millimeter can mean misalignment that'll show up during operation as severe vibrations. And vibrations at this power level aren't just an inconvenience, they're a disaster. When the rotor hangs over the open capsule, the most nerve-wracking phase begins. They literally lower it millimeter by millimeter, constantly measuring clearances with laser instruments. Inside the housing, bearings and support elements are already installed, and everything has to align to within thousandths of a millimeter. If the engine shaft is even slightly off from the geometric center of the capsule, a spinning imbalance will develop that the entire ship will feel. At operating speed, this imbalance turns into a constant hammering that can destroy bearings or damage the housing from the inside in a matter of weeks. After the rotor is seated, engineers won't allow the crane to be removed for a long time. A series of checks begins. They measure alignment, manually rotate the shaft several times, listen carefully to the sound of metal. The slightest unusual noise and the part gets lifted back up. Sometimes they raise the motor again and adjust its position, spending hours for just a few millimeters of correction. Everyone here understands. Once the capsule is sealed, there will never be access inside again, so perfect precision matters more than any installation speed. When the motor finally settles into place, the entire structure suddenly looks complete. An empty steel shell transforms into a real propulsion system. This is the moment you can consider the birth of a system that will later spin the propeller, turn a multi-thousand-ton vessel, and operate for years underwater, where no human will ever see it again. Modern units can pump out up to 22 megawatts of power. That's the equivalent of more than 30,000 horsepower. To put that in perspective, a single engine like this could supply electricity to a small town of 25,000 people. And this is a mechanism that operates completely underwater, hidden from view, impossible to service in the open ocean. It's designed with reliability margins years into the future because scheduled maintenance is only possible in dry dock. A fully assembled unit with engine and propeller can weigh over 320 tons. The propeller that attaches to the pod often exceeds 23 feet in diameter. Each blade on a propeller like that weighs as much as an adult African elephant. Yet this entire system has to run absolutely smooth. Any vibration at these power levels instantly transfers to the hull and gets felt by passengers on every deck. Once the engine is safely tucked inside its steel housing, the final stage begins, installing the propeller. If the pod itself is the muscle, then the propeller is the hands that push against the water and drive the ship forward. Each blade is manufactured from a special alloy of bronze, aluminum, and nickel. This metal needs to be strong enough not to bend under the pressure of thousands of tons of water, yet smooth enough not to create unnecessary turbulence. The blades arrive at the pod on special pallets, each wrapped in protective film like a piece of jewelry. Installation is carried out using hydraulic rams. The propeller is mounted onto the engine shaft protruding from the pod, and here precision is once again measured in thousandths of a millimeter. Any misalignment will cause the propeller to vibrate at operating speed, and that vibration will destroy the engine bearings within days. When the propeller finally locks into place, it's secured with a massive nut, tightened with several thousand Newton meters of torque. After that, a streamlined cap is installed on the hub to ensure the water flow past the propeller is perfectly smooth. The entire assembly is coated with special paint that marine organisms and barnacles won't stick to. Because even a few centimeters of buildup on the blades can reduce engine efficiency by 5 to 7%, translating to losses of hundreds of thousands of euros per year. Every second, the world produces 28 million tons of stainless steel. And behind the shine of every spoon, every faucet, every surgical instrument stands one metal: chromium. But here's what's mind-blowing. Chromium melts at 3,375 degrees Fahrenheit, and in the electric arc furnaces that produce it, temperatures hit 5,000 degrees, hotter than the surface of the sun. A single furnace consumes 4,000 kilowatt hours of electricity per ton of alloy. That's as much as the average apartment uses in 4 months. 80% of all chromium in the world goes into making stainless steel. But where does this metal come from? Why are 99% of the world's chromite reserves concentrated in just a handful of countries? And what happens in that hellish zone beneath the electrodes, where ore transforms into molten ferrochrome? Stick around. You'll discover how black rock gives birth to the metal that makes steel immortal. Picture a massive electric arc furnace as tall as a 3-story building. 3 carbon electrodes up to 6 feet across plunge into a churning mass of glowing ore, coke, and fluxes. Between the electrode tips and the furnace floor, electric arcs crack and snap. Temperatures in this zone hit 5,000 degrees Fahrenheit. That's hotter than the surface of the sun. The air above the furnace shimmers with heat. Clouds of smoke and gas blast out from beneath the half-closed roof. Inside, real alchemy unfolds. Chromium ore mixed with coke melts down, oxygen escapes as carbon monoxide, and molten ferrochrome, an alloy of chromium and iron, flows to the bottom. This is a submerged arc furnace, and this is where most of the world's ferrochrome is born. The process runs non-stop. Fresh batches of ore and coke pour in from the top, molten metal and slag tap out from the bottom. A single furnace like this can pack 25 to 45 megavolt amperes of power. This is a monstrous amount of energy. An entire power plant runs just to melt the ore. When enough molten ferrochrome accumulates in the furnace, workers punch open the tap hole, a special opening in the furnace's side. And then the mesmerizing spectacle begins. A stream of white-hot metal and slag bursts out, flowing down a channel into an enormous ladle. The stream's temperature around 3,000 degrees Fahrenheit. The metal glows bright orange, almost white. The heat radiating from it is so intense that workers stand dozens of yards away, protected by special screens and fireproof clothing. Slag floats to the top and is drained off separately. The ferrochrome cools in massive molds, transforming into solid ingots weighing hundreds of pounds. These ingots are later crushed into pieces of the right size for sale to steel mills. But the process of obtaining ferrochrome, that's only the middle of the journey. It all begins with ore, mined deep in the earth. Chromite, the only industrial ore of chromium. It's a dark brown, almost black mineral with a metallic luster. The chemical formula? Iron and chromium oxide. Pure chromite contains 68% chromium oxide and 32% iron oxide. But in nature, perfect ores like that barely exist. Real deposits contain anywhere from 40 to 50% chromium oxide. Chromite forms in igneous rocks, in massive molten masses rising up from the Earth's mantle. The largest deposits are found in South Africa, Kazakhstan, India, and Turkey. These 4 countries account for roughly 80% of global production. South Africa is the absolute leader. Its deposits in the Bushveld complex contain 200 million tons of chromite. We're talking ore seams stretching for hundreds of miles and plunging thousands of feet deep. Kazakhstan holds reserves of 230 million tons. India? 54 million tons. Now the story. French chemist Louis-Nicolas Vauquelin discovered chromium in 1797. He isolated it from croquat, a bright red lead chromate mineral. The mineral's vivid color inspired Vauquelin to name the metal after the Greek word chromos, color. Because chromium compounds produce stunning colors, greens, yellows, oranges, reds. A year later, in 1798, Vauquelin isolated pure chromium by reducing the oxide with carbon. Iron with added chromium was first produced in the mid-1800s, and the first use of chromium as an alloying element in steel production happened in France in the 1860s. The revolution came in 1893 when Henri Moisson smelted chromium ore with carbon in an electric furnace and produced ferrochrome. This became the foundation of the modern industrial method, which has evolved but at its core remained the same. Chromite gets mined both through open-pit operations and underground mines. Open-pit mining gets used when the ore sits close to the surface. Giant excavators strip away the soil and overburden, exposing the chromite layers. Then they blast the ore, load it into haul trucks with capacities up to 300 tons, and transport it to the processing plant. Underground mining gets deployed for deep deposits. Tunnels get driven hundreds of feet down, sometimes miles. They blast the ore, load it into mine cars, and haul it to the surface. The extracted ore? It's not pure chromite yet. It comes mixed with waste rock and other minerals. That's why the ore needs processing. First, they crush it in massive jaw crushers. Chunks the size of a car get reduced to fist-sized pieces. Then they grind it in ball mills down to the size of sand or even dust. After that comes separation, isolating the chromite from the waste rock. The main method for enriching chromite is gravity separation. Chromite is heavier than waste rock. Its density is 4.5 to 4.8 grams per cubic centimeter, while the rock is 2 to 3 grams. The crushed ore is mixed with water, creating a slurry. The slurry passes through jig machines, concentrating tables, spiral classifiers, centrifugal separators. Under the force of gravity, the heavier chromite grains settle faster, while the lighter waste rock is carried away by the water flow. Magnetic separation is also used. Chromite is weakly magnetic, but modern high-intensity magnetic separators can attract it and separate it from non-magnetic impurities. After enrichment, they obtain chromite concentrate containing 46% or more chromium oxide. This is ready-made raw material for metallurgy. The concentrate is dewatered, dried, and sent to ferroalloy plants. Lump ore is needed for ferrochrome production. Fine powder doesn't melt well in the furnace. So the fine particles get agglomerated, sintered into large chunks. They mix the concentrate with fluxes and coke breeze, moisten it, and form pellets. Then they heat it to about 2,200 degrees Fahrenheit. The pellets sinter into solid lumps a couple inches across. Now the ore is ready for smelting. At the ferroalloy plant, chromite concentrate gets mixed with coke and fluxes in specific proportions. Coke is the carbon source that'll reduce the oxides down to metal. Fluxes, quartzite, dolomite, limestone, are needed to form slag with the right composition and melting point. The charge, the mix of ore, coke, and fluxes, gets loaded into the electric arc furnace from the top through special hoppers. Loading happens continuously or in batches depending on the furnace type. The electrodes, massive carbon cylinders, are submerged in the charge layer. When they switch on the current, an electric arc forms between the electrodes and the material beneath them. Temperature in the arc zone? 5,000 degrees Fahrenheit and higher. That's enough to melt any ore. Inside the furnace, complex chemical reactions take place. Carbon from the coke combines with oxygen from chromium and iron oxides, forming carbon monoxide that rises upward. Chromium and iron are reduced to their metallic state and fuse together, forming ferrochrome. Some of the carbon dissolves into the metal, producing high-carbon ferrochrome with a carbon content of 4 to 8%. Typical South African ferrochrome contains 52 to 54% chromium, 6 to 7% carbon, and 2 to 4% silicon. Ores from Zimbabwe with a higher chromium to iron ratio yield a product with 63 to 67% chromium. The molten ferrochrome and slag accumulate in the lower part of the furnace, the hearth. When enough metal has built up, they open the tap hole. Metal and slag flow into a ladle. The slag floats to the top and is poured off or skimmed away. The metal is poured into molds or cooled in special forms. Once solidified, the massive ingots are broken down by hydraulic presses or hammers into pieces of the required size. Ferrochrome production is incredibly energy intensive. A single ton of high-carbon ferrochrome burns through 2,000 to 4,000 kilowatt-hours of electricity. That's why ferrochrome plants get built in countries with cheap power, often right next to hydroelectric dams. Chromium recovery from ore hits about 90% under good conditions. The remaining 10%, it goes into slag. Slag isn't just waste. Metal particles get extracted from it using mineral processing methods, and what's left goes into construction. Ferrochrome isn't the end product. It gets shipped to steel mills where it's added to molten steel for alloying. Chromium gives steel corrosion resistance, hardness, heat resistance. Stainless steel contains 10 to 20% chromium. Average, 18%. It's chromium that forms a thin, invisible oxide film on the steel's surface, protecting the metal from rust. And so, having traveled from black rock in the Earth's depths through quarry explosions, crushing and processing, through the inferno of an electric arc furnace at 5,000 degrees Fahrenheit, ferrochrome is born. An alloy that gives steel eternal life and shine, resistant to time and corrosion.
Every year, people around the world devour over 50 billion pieces of fried chicken, millions of burgers, and 1 billion pizzas. But hardly anyone stops to think about what's behind those perfectly golden crusts and aromas we've come to take for granted. What if I told you that inside these flavor factories, technologies operate with more precision than surgical instruments, and recipes are guarded more closely than military secrets? In this video, you'll see how the food the entire planet loves is made, from KFC's secret blend of 11 herbs and spices to Domino's billion pizza assembly line. Stick around until the end, and you'll learn things they've never revealed, even in their advertising.
Do you love KFC fried chicken as much as I do? Its story doesn't start in a fryer, but on massive American farms where chickens are raised under the strictest safety standards. After arriving at the plant, each bird flows through a cascade of automated systems. Artificial intelligence, like a vigilant guardian, analyzes images from high-resolution cameras, filtering out any defects. This isn't just a conveyor belt. This is a river of raw material,
flowing through an incredibly complex control system. Only the best specimens, passing this digital selection, move to the next stage. This is the first level of guarantee that every single piece will be perfect.
What follows is a processing stage that resembles a high-tech ballet. The carcasses are plunged into water at a precisely calibrated temperature of 140 degrees Fahrenheit to soften the feathers. Then, automated machines equipped with thousands of rubber fingers spinning at tremendous speed strip away the plumage in seconds. These units can process up to 10,000 carcasses per hour. After that, laser-guided robotic cutters divide the carcasses into 9 standard parts with surgical precision, no more, no less. Every single piece gets weighed, scanned, and assigned its own digital footprint in the production management system.
But here's where things get really interesting. The chicken gets marinated in a special brine that makes the meat incredibly juicy. And then comes the sacred ritual, the breading. That legendary secret blend of 11 herbs and spices, a recipe Colonel Sanders developed way back in 1940, remains one of the most closely guarded trade secrets in the world. Where it is, the original recipe sits in a vault at KFC headquarters. The blend ships to factories in 2 separate bags, and they only mix the contents right before breading. The breaded chicken gets fried in special pressure fryers at 375 degrees. It's that pressure that locks in the juiciness inside while creating that iconic crispy coating outside. If beef's more your style, welcome to the world of the Big Mac. McDonald's uses only 100% beef from verified suppliers. After rigorous inspection, the meat's ground and formed into patties weighing exactly 1.6 ounces. This precision isn't a quirk, it's what guarantees each patty cooks perfectly. To preserve freshness without preservatives, the patties undergo flash freezing at 0 degrees Fahrenheit. This allows ice crystals to form instantly without damaging the meat structure. Big Mac buns are baked on automated lines, where the dough is mixed, shaped, and topped with exactly the amount of sesame seeds the standard requires. Vegetables, crispy iceberg lettuce, onions, pickles, go through multiple rounds of washing and slicing. But the real secret of the Big Mac? That's the sauce. Its exact recipe is another mystery, guarded like classified intel. In restaurants, frozen patties get seared on a double-sided grill at 425 degrees for just 42 seconds. That's the perfect window. Golden crust on the outside, juicy meat inside. Then the crew, like soldiers on an assembly line, stacks the burger in strict order in mere seconds. That's why this icon of an era has stayed exactly the same for over 50 years. Did you know the Domino's pizza story started with a $500 debt? In 1962, 2 brothers bought a small pizzeria in the American town of Ypsilanti. Their main promise, which became the driving force of the entire industry, pizza delivery in 30 minutes. This rule sparked a revolution. Today, everything starts with the dough. At giant facilities, flour, water, yeast, and oil get mixed in industrial mixers. The dough rises in chambers with controlled humidity and temperature. Then it's divided into portions, shaped into round bases using presses, and flash frozen.
That's what makes it possible to deliver identical dough to thousands of pizzerias around the world.
Tomato sauce is made from specially grown tomato varieties that get processed into puree within hours of harvest. Mozzarella is shredded on industrial graters, and pepperoni is sliced with laser precision. Sauce gets spread on the base, cheese is sprinkled on top, and exactly the number of pepperoni slices required by the standard gets laid out. Then the pizza heads into a conveyor oven at around 500 degrees Fahrenheit. Domino's Pizza is the world's largest pizza chain, cranking out roughly 1 billion pizzas every year. Their newest automated dough production center in Indiana can produce enough raw dough for tens of thousands of pizzas daily.
But how does all this food produced in giant factories make it to our table while staying fresh and flavorful? Behind it lies an invisible yet incredibly complex system, cold chain logistics. It's the actual nervous system of the global fast food empire. Frozen patties for the Big Mac and chicken for KFC travel in special refrigerated trucks where the temperature is maintained at -4 degrees Fahrenheit, accurate to within a degree. Sensors transmit temperature data to a central server in real time. Any deviation, the system sounds the alarm. Buns, vegetables, and sauces are transported in separate compartments at their own optimal temperatures. It's a whole science ensuring products don't thaw and refreeze, which destroys their texture and flavor.
Why does a Big Mac in Tokyo taste exactly like one in New York? The secret lies in sensory analysis science and obsessive consistency. Every major company has what are called sensory panels, teams of specially trained tasters with superhuman taste and smell. Their job? Sample products and compare them against the gold standard, a reference sample stored in the lab. They evaluate dozens of parameters: the saltiness of the sauce, the crunch of the lettuce, the softness of the bun, the aroma of the patty. Any deviation from the standard, even the slightest, and the entire batch can be rejected. It's a genuine flavor DNA code that companies replicate and reproduce worldwide. So no matter where you are, you always get that same familiar taste from childhood. So what's the main secret promised at the start? It's not 11 herbs and spices, and it's not some sauce recipe. The real secret these giants are hiding is creating consistency. It's psychology. The secret is they're not just selling food, they're selling comfort. In a world full of uncertainty, you always know exactly what your Big Mac or chicken wing will taste like. This isn't just lunch, it's an anchor of stability, a flavor that hasn't changed in years and decades. They took the most complex processes, from animal genetics to global logistics to flavor chemistry, and packaged them in a simple cardboard box. And they made us believe it's simple, fast, and always tastes the same. And that's their real genius.
Hey everyone, on this channel we go behind the scenes where cameras usually aren't allowed. If you're into this kind of breakdown, hit subscribe and tap that bell so you don't miss new episodes. Every year, the world recycles over 1.5 billion tons of scrap metal, and hidden within this chaos of rust and mangled iron is something way more valuable than it looks. What seems like trash today could save your life tomorrow at 75 miles per hour. But how exactly does this pile of metal transform into a precision-engineered component trusted by millions of drivers? And why can even a tiny 1% error destroy an entire batch? There's one detail in this process almost nobody talks about, and it's what determines whether your car stops when it really matters. Today, we're breaking down the entire production of brake rotors, from the furnace to final inspection. It all starts with what most people would just call a junkyard. And that's pretty ironic. What will later stop your car at 75 miles per hour, right now looks like a giant pile of rusty junk. Old cast iron radiators, car body fragments, twisted beams, and other metal scrap. It's all stacked in heaps on the lot outside the plant, and rain sends rusty orange streaks running down into the asphalt. But to this factory, it's all treasure. A massive electromagnet hanging from a crane scoops up several tons of this iron and drops it with a crash into the throat of a giant induction furnace. Induction, meaning the metal doesn't melt from fire, but from an electromagnetic field that heats it from the inside out, evenly and fast. If you stand too close, it's kind of terrifying. The furnace hums at such a low frequency that you don't really hear the sound. You feel it deep in your chest, like your heart's trying to sync up with this heavy industrial rhythm. The temperature inside the furnace climbs to 2,700 degrees Fahrenheit. At that kind of heat, even the toughest steel turns into liquid, more like glowing, ridiculously dangerous soup than anything solid or dependable. When the furnace tilts to pour out the molten metal, everything around you floods with bright orange light that makes you want to squint. No artificial beauty here, just brutal physics and an insane amount of heat. Every batch of metal gets tested instantly. Lab techs in special suits grab a small sample, cool it down, and within seconds determine its chemical makeup using a spectrometer. The device breaks the sample down into elements and spits out precise percentages of each component. If the carbon or silicon content deviates from spec by even 1%, the entire massive batch gets sent back for remelting without hesitation. Mistakes aren't tolerated here, because the cost of that kind of error to the end user could be way too high. Next, they pour this liquid fire into molds. They use sand casting technology here. Sand seems like an unreliable material, but at this factory, they mix it with special resins and under enormous pressure, it becomes hard as concrete. The molds are made with jeweler-like precision. The internal relief copies every detail of the future disc, including cooling fins and mounting holes. Metal fills the cavities inside the sand mold, and it's at this exact moment that the rough blank of the future brake disc is born. It doesn't look anything like that shiny part we're used to seeing in auto parts stores yet. Instead, it's something big, heavy, and really dirty. After pouring, the discs need to cool naturally. It's a long process, sometimes taking several hours, and this is critically important. If you try to speed up the cooling, say by splashing water on it, the metal becomes too brittle. A disc like that could just shatter into pieces at the first hard stomp on the brake pedal somewhere out on the highway in the rain. When the blanks cool down to just warm instead of glowing red hot, they head to the machining shop. This is where robot territory begins. They work 24/7, no lunch breaks, no complaints about tough working conditions. Each disc gets grabbed by a manipulator arm that loads it into a CNC machine. Special cutting tools shave off excess metal as easily as if it weren't solid cast iron, but a stick of cold butter. Chips spiral out red hot and drop into a collection tray while a smooth, precisely calibrated surface emerges from under the cutter. At this stage, fanatical precision rules. A deviation of 0.8 of a millimeter means hopeless scrap. A disc like that never makes it to the warehouse because it'll cause vibration that'll just destroy a car's suspension in a few months and force the driver to shell out a ton of cash for repairs. The machine finishes one disc in several minutes, and each one comes out identical to the last. Robots don't get tired and don't lose focus by end of shift. It's fascinating to watch as the perfect, almost mirror-like surface gradually emerges from a rough and ugly form. Then they drill ventilation holes and internal channels into the discs. This isn't done for visual style like some people think. It's a critically necessary cooling system, without which the discs simply wouldn't survive serious loads. During heavy braking, the disc can heat up to 1,300 degrees Fahrenheit. At that temperature, it glows dark cherry red. If this heat isn't removed in time, the metal starts losing its friction properties, and the brakes just disappear at exactly the wrong moment. So these holes and channels, they're the result of extensive engineering calculations, not some design decision for looks. Each channel has a precisely determined diameter and angle, calculated so airflow pulls heat away from the working surface as efficiently as possible. Once all the excess shavings are removed, each rotor gets sent to dynamic balancing. It's a lot like what they do to your wheels at the tire shop, but the precision here is tens of times higher. A special device spins the rotor up to enormous speed and uses sensors to detect the slightest weight imbalance. At these rotational speeds, any imbalance turns into noticeable vibration, and the machine picks it up with gram-level accuracy. If one side turns out to be heavier by even 3 or 4 grams, the machine automatically drills out a tiny, nearly invisible dimple in just the right spot on the face to even out the weight. After that, the rotor is perfectly balanced and ready to perform at any RPM without any extra noise or judder. It's at this stage that the difference is made, whether the driver will feel every imperfection through the pedal or whether braking will stay smooth and silent at any speed. I asked the chief engineer how many of these rotors they produce in a single full workday. He just smiled wearily and said they stopped counting them individually a long time ago. They track output in thousands of tons of finished product per month. Just think about that for a second. This facility supplies parts for nearly half the European automotive market, which means every other car you see on city streets is probably stopping with rotors made right here, in this loud, scorching hot plant. Before packaging, the rotors go through a protective coating process. They're either painted with a special heat-resistant paint or coated with a thin, anti-corrosion, zinc-based layer. The coating gets applied in a chamber, the rotor hangs from a conveyor, and automatic sprayers evenly cover it from all sides. This is done so they don't turn into a rusty chunk of metal during long-term warehouse storage or while crossing the ocean in a shipping container. Sure, after the first few miles of driving, this paint on the working surface will completely wear off under the massive friction from the brake pads, but the edges and internal parts will stay protected from road salt and grime. The final, and arguably most critical stage, is the quality control check. And we're not talking about some tired worker giving it a quick once-over at the end of their shift. They use ultrasonic scanners and X-ray machines. They're hunting for internal defects, air bubbles or micro cracks you couldn't spot even with a magnifying glass. Ultrasound sends a wave through the metal, and if there's a void inside, the signal bounces back distorted. The machine flags the problem zone instantly. Even if the disc looks flawless on the outside, but the X-ray reveals a cavity just 2 millimeters wide somewhere deep in the metal, it gets sent straight to the shredder. Nobody cuts corners on safety here, because everyone knows full well, this part directly determines whether the driver and passengers live or die.
Every year, Japan produces millions of tons of steel, but only a fraction of it becomes the heart of what is considered a modern engineering miracle, the rails for the Shinkansen bullet trains. Imagine a furnace larger than a 5-story building, heated to over 1,500 degrees Celsius, where iron and carbon boil. This ocean of fire is transformed into rails the length of a football pitch, so perfectly straight that the smooth glide of a train at 320 kilometers per hour depends on them. But the real secret lies in how Japanese engineers fuse these rails into a continuous ribbon, up to 1.5 kilometers long. Do you want to know how they created the illusion of an endless rail without a single click-clack? Watch until the end. We are inside a vast Japanese steelworks. The atmosphere is heavy, thick with a mixture of intense heat, the smell of steel, and the deep hum of powerful machinery. Before us stands the main character of this scene, a steel-making furnace the size of a 5-story building. It resembles the mouth of a volcano, glowing a blinding white. Inside, a boiling mixture of iron and carbon churns at over 1,500 degrees Celsius. With a roar, the molten metal is poured into special molds, like a brilliant orange river of lava flowing down a mountainside. Against the scale of these immense machines, the workers look tiny. After the steel is cast, it begins to cool, transforming from a liquid into a solid, yet still intensely hot block of metal. The rolling mill is a colossal machine, something like a giant meat grinder, but instead of blades, it has heavy steel rollers that crush and stretch the metal. The deep rumble intensifies as the machine grips a red-hot billet. With a sound like a low groan, the hot steel begins to elongate, like dough for pasta, but dense and heavy. Gradually, this billet becomes longer and straighter until it finally emerges as a single continuous rail, almost 100 meters long, the length of a football pitch. The surface of such a rail must be absolutely flawless, without the slightest ripple. Because if it is even minutely uneven, a Shinkansen train will not glide smoothly over it. After rolling, the rail is still incredibly hot. Steam rises from it, and you can hear a crackling sound, like water hitting a scorching hot plate. But this is its almost finished form: long, heavy, smooth, ready for inspection, grinding, and its future life. To reduce the number of joints, Japan uses a method of continuous welding, where several rails are fused into one extremely long ribbon. The welding of rails for high-speed trains like the Shinkansen is a high-precision process, with the goal of turning individual sections into a seamless track up to 1.5 kilometers long. It is this type of joint that eliminates the traditional click-clack sound as the train passes over it. The welding process occurs in several stages. The most common method is thermite welding, a reliable and visually spectacular technique. Two rails are positioned end to end, with a gap of just a few millimeters between them. The surfaces of the future joint are meticulously cleaned of any rust or contaminants. A special mold made of a heat-resistant material is then clamped around the joint. A small crucible above the joint is filled with the thermite mixture, a powder of aluminum and iron oxide. When it is ignited, a chemical reaction occurs, generating a temperature of over 2,500 degrees. The result is molten iron, which flows down and fills the gap between the rails, fusing them at a molecular level. The reaction lasts several minutes, accompanied by a hissing, crackling sound as a brilliant flame erupts above the joint. It looks like a miniature volcanic eruption. After the metal solidifies, which takes about 10 minutes, the mold is removed and the excess metal is sheared off. The joint is then ground down to a perfectly smooth surface so that the train wheel feels no transition. The finished weld is inspected with laser measurements and ultrasonic sensors which search for any potential micro cracks. In a world where every second counts, Shinkansen engineers discovered the secret to permanence, the slab track. Instead of traditional stone ballast, they created monolithic giants from concrete. These Titan slabs can reach a thickness of 66 centimeters, the height of 2 footballs stacked on top of each other. Japanese masters also invented an ingenious solution: encapsulation units. Imagine a metal cradle that embraces the rail like a mother holds a child. These cradles not only secure the steel tracks, but also isolate them from vibration and electricity. But the most brilliant part of the system is what you cannot see. Between the concrete slabs and the foundation, the Japanese placed resilient layers that act as giant shock absorbers. Transporting the sleepers to the installation site is done in several ways. For short distances, special crane-equipped lorries are used. For longer routes, railway flatbeds. Safety during transport is critical. A single concrete sleeper must be lifted by 4 workers, highlighting their significant weight, roughly 75 kilograms per worker. For mechanized lifting, special grabs and cranes are used. On the construction site, the installation process begins with the preparation of the base. For the slab track, which is predominantly used on the Shinkansen, the sleepers are installed onto precast concrete slabs. Each sleeper is positioned with an accuracy of 6 millimeters, as even the slightest deviation can cause problems at speeds of 320 kilometers per hour. The installation is carried out by specialized crews using precision equipment. First, support points are set every 60 centimeters, the standard interval for high-speed lines. Each sleeper is then fixed to the base with special anchor bolts, 2.5 centimeters in diameter, which are driven 15 centimeters deep into the concrete slab. The process is further complicated by the need to integrate with the power supply and signaling systems. The final stage involves installing vibration insulating pads between the sleepers and the base. These rubber steel elements significantly reduce the transmission of vibrations from the trains to the surrounding structures. After the installation is complete, the entire section is tested by a special inspection train. Despite more than 120,000 trains running on the line annually, the average delay is just 36 seconds. Over half a century, the top speed has increased from 210 to 320 kilometers per hour, and the line now carries 1 million passengers a day. A new line is expected to operate at 500 kilometers per hour, with a projected journey time between Tokyo and Osaka of just 67 minutes.
Picture this. Glass that once shattered into deadly shards now saves lives. How did humanity transform a fragile substance into armor for your car? Every year, the world produces over 100 million square meters of automotive glass, enough to cover an entire country. But the real magic happens where molten rock becomes a perfectly smooth surface, in furnaces reaching temperatures over 2,700 degrees Fahrenheit. That's hotter than the surface of molten lava. How did ordinary quartz sand become the foundation of a safety technology we can't imagine modern transportation without? What accidental experiment changed the history of automobiles forever? You'll discover how the first safety glass was created, what secrets hide within its layers, and why modern windshields can withstand the impact of a rock at 60 miles per hour. Watch until the end. The finale reveals how many stages glass goes through to protect your life. The history of automotive glass production is closely tied to the development of the automobile industry, which emerged in the late 19th century. When the first cars began appearing on roads, they weren't equipped with glass at all. The open body design only partially protected passengers, while dust, wind, insects, and other hazards made trips extremely uncomfortable. Later, as cars got faster, the need arose to install protection for drivers and passengers. Windshields started being made from ordinary window glass, which, while providing some protection, had a serious flaw. During accidents, it shattered into large, sharp shards, leading to numerous injuries and deaths. Glass sliced faces, necks, arms of drivers and passengers. This was a real problem demanding an urgent solution. The first revolutionary breakthrough in automotive glass came with the creation of laminated glass, and it happened by accident. In 1903, French chemist Edouard Benedictus accidentally knocked over a flask coated with nitrocellulose. The glass cracked, but stayed intact thanks to a thin plastic layer. This accident inspired the scientists to create multi-layer glass, which later became the foundation for laminated safety glass. By the 1910s, laminated glass started appearing in premium automobiles. Its construction consisted of two glass layers with a thin, transparent film sandwiched between them. On impact, the glass wouldn't shatter. Cracks would stay trapped in the film. In the 1920s, laminated glass became widely used in windshield production. Its main advantage? Enhanced safety. Even in serious crashes, fragments wouldn't fly everywhere. They'd stay locked in the polymer layer. The next stage in automotive glass development came in the 30s, when tempered glass manufacturing technology was patented. This material was produced by heating glass to high temperatures followed by rapid cooling. As a result of this process, the glass became stronger, and when it shattered, it broke into small pieces with blunt edges, minimizing injuries. In the mid-20th century, tempered glass began to be used for side and rear car windows. It was cheaper to produce compared to laminated glass and provided a sufficient level of safety for these parts of the vehicle. In the 50s and 60s, automotive glass became even more advanced thanks to technological developments. Important changes occurred. Improvements to laminated glass and the development of new polymer films made laminated glass more transparent, resistant to ultraviolet radiation, and durable. Mass production and automation of manufacturing processes allowed for a reduction in the cost of automotive glass. One of the biggest technological breakthroughs in glassmaking came in 1959 with the invention of the float process. This technology, developed by British company Pilkington, made it possible to manufacture perfectly smooth glass by spreading molten glass across a surface of molten tin. Picture this. Red-hot liquid glass pours onto a mirror-like surface of molten metal and spreads itself out, forming a perfectly flat sheet. Thanks to this method, glass became more uniform, stronger, and accessible for mass production. The float process is still the foundation of automotive glass manufacturing today, ensuring precise dimensions, smooth surfaces, and high quality. In the second half of the 20th century, automotive glass underwent even more changes aimed at improving safety and comfort. In the 60s, heating wires started being installed in rear windows to prevent fogging and freezing. In the 80s, glass with special metallic coatings appeared that reflected sunlight and reduced cabin heating. UV protective glass, thanks to new technologies, began providing nearly complete protection from harmful radiation. Modern automotive glass is divided into several types depending on its purpose and manufacturing technology. The windshield is typically laminated glass consisting of 2 layers of glass with a polymer film sandwiched between them. This design ensures that when damaged, the glass doesn't shatter into sharp fragments. Side and rear glass are most often tempered glass, which breaks into small blunt pieces upon impact, reducing injury risk. Panoramic roofs or other specialty glass types often use laminated or tempered glass with special coatings for ultraviolet radiation protection. The main components of glass are natural materials mixed in specific proportions to achieve the desired properties. Quartz sand is the primary ingredient of glass, providing its transparency. It must be extremely pure with minimal impurities. Soda is added to lower the melting point of glass. Lime improves the mechanical strength and chemical properties of glass. Additional additives are used to adjust color, transparency, resistance to ultraviolet light, and other characteristics. The raw materials are purified, dried, and ground to a uniform consistency. It's critical that impurities that could affect glass quality are eliminated as much as possible. After the raw materials are prepared, they're loaded into specialized furnaces for melting. The melting temperature to form glass reaches around 5,000 degrees Fahrenheit. This is the temperature at which stone transforms into liquid. During the melting process, the raw materials become a uniform, viscous fluid. The glass mixture gets stirred to distribute components evenly. This matters. You want to avoid air bubbles or inconsistencies in the finished product. Glass melting furnaces come equipped with modern temperature control systems and process automation, ensuring top quality end results. After melting, the glass mass undergoes forming, which in modern production is most often done using the float process. Liquid glass flows out of the furnace and enters a bath of molten tin. Thanks to tin's high density, the glass mass spreads evenly across its surface. Under its own weight, the glass forms a perfectly flat and smooth surface. Gradually lowering the temperature, the glass hardens. By the time it exits the bath, it's ready for processing. The float method allows manufacturers to produce glass sheets with precise geometric parameters and high surface quality. After cooling, the glass sheets are cut according to the dimensions needed for automotive production. Automated cutting machines ensure precision in the process. To prevent cracks and chips, the glass edges are ground down. Each sheet undergoes inspection for defects like microcracks, bubbles, or other damage. To guarantee the strength and safety of automotive glass, it goes through a tempering process. The glass is heated to around 1,112 degrees Fahrenheit. Then the glass surface is rapidly cooled by air jets, while the inner layers cool more slowly. This creates tension that increases impact resistance. When tempered glass breaks, it shatters into small, safe fragments, minimizing the risk of injury. Windshields use laminated glass, a construction of glass and polymer film. Its manufacturing involves several steps. A polymer film is placed between 2 glass sheets. The construction is put into a vacuum press to eliminate air bubbles. Next, the glass is heated in an autoclave to 284 degrees Fahrenheit under high pressure. This creates a rock-solid bond between the layers. Laminated glass has exceptional impact resistance, and when damaged, it stays held together by the polymer film, keeping drivers and passengers safe. To enhance automotive glass properties, various coatings are applied. Anti-glare coatings reduce reflections from the sun or headlights of other cars. UV protection, special layers block harmful ultraviolet radiation. Hydrophobic coatings make water sheet right off the glass surface. Heating elements, thin heating wires can be embedded in the windshield, making it easier to clear ice or fog. To achieve the exact shape needed, special thermoforming equipment is used. The glass is heated to a temperature where it becomes pliable and is formed according to the specified parameters. In the final stage, every piece undergoes rigorous inspection. They check for clarity and defects. The glass is tested for impact resistance and load endurance. Standards compliance, dimensional accuracy, shape, and other parameters are verified. The finished automotive glass is packaged to prevent damage during transport. It's shipped to auto plants or service centers where it's installed in vehicles. And that's how, journeying from quartz sand through the hellish flames of furnaces at 5,000 degrees Fahrenheit, through a bath of molten tin, through tempering and lamination, glass is born, capable of protecting life at 75 miles per hour. This is the story of how an accidentally shattered flask changed the automotive world forever. Automotive glass production is a high-tech process combining physics, chemistry, and engineering. Thanks to modern technology and strict quality control standards, automotive glass delivers safety, comfort, and durability. Every time you get in a car, remember, between you and danger, a thin layer of glass that's passed through dozens of production stages to save your life in that critical moment.
Your smartphone would weigh over 2 pounds and be an inch thick. A can of Coke would cost $5. A Boeing 747 couldn't cross the Atlantic. It'd run out of fuel halfway. And half the stuff in your house simply wouldn't exist. All because of one metal that humans didn't discover until 1828 and couldn't mass produce until 1886. Before that, the world ran on iron, steel, copper, and bronze. Metals too heavy, too expensive, or too weak for modern life. Today, we're heading inside an aluminum plant, and I'll show you what properties emerge at each stage. This aluminum plant sits right on the riverbank. That's no accident. It's been running non-stop for over 120 years. It's here because it has direct access to massive hydroelectric power. That's critical because making aluminum takes more electricity than almost any other industrial process on Earth. Walk onto the grounds and the first thing you feel, a low hum from the transformers. The smell of superheated metal hangs in the air constantly. The plant never stops, not for a minute. The raw material is bauxite, a reddish-brown powder that arrives on ships from tropical countries, Jamaica, Australia, Guinea. If aluminum had never been discovered, we'd still be mining iron ore for everything. Steel production needs coal. It gives off massive emissions. Aluminum here, it runs on clean hydropower. Without aluminum, global carbon emissions would be roughly 15% higher from metal production alone. The first stage is processing bauxite through the Bayer process. The ore is crushed and mixed with caustic soda, then heated to 347 degrees Fahrenheit under pressure in autoclaves. Under these conditions, aluminum oxide dissolves while iron and silicon remain as red mud, a thick, bright, rust-colored mass that's diverted to special storage facilities. The output? Pure white aluminum oxide powder, also known as alumina. To produce 1 ton of alumina, you need to process about 2 tons of bauxite. This is where aluminum's first critical property is established: incredible corrosion resistance. In air, aluminum instantly forms an ultra-thin oxide film that locks the metal into protection against further oxidation. If we use steel, every outdoor structure would need constant repainting. Steel ships require dry dock and repainting every few years. Aluminum boats serve for decades without maintenance. Without this property, coastal cities would burn billions on infrastructure upkeep. The alumina is moved to the electrolysis hall, and this place is impressive. A massive room with rows of reduction cells radiating waves of heat. These are glowing rectangular pools about 15 feet long, filled with molten cryolite at a temperature of around 1700 degrees Fahrenheit. The surface of the cells flickers orange, and the air shimmers from the heat. The alumina dissolves in this bath. Then, a current of 150,000 amps is run through each cell, enough electricity to power 15,000 homes. The current rips aluminum atoms away from oxygen atoms. Pure molten aluminum sinks to the bottom. Oxygen rises to the top. This is the Hall-Héroult process, invented in 1886, and it's still the only economically viable way to produce aluminum. Before it, aluminum cost more than gold. Napoleon III used aluminum plates for his most important guests, while everyone else ate from gold ones. Without the Hall-Héroult process, aluminum would cost hundreds of dollars per pound today, and a can of soda would set you back a fortune. After a full day of operation, the molten aluminum gets pumped out and poured into crucibles, 10 tons each. The liquid metal glows with a soft, silvery light, nothing like orange cast iron or golden bronze. This shimmering metal demonstrates aluminum's most critical property, strength-to-weight ratio. Aluminum's 3 times lighter than steel, but with the right alloying, nearly as strong. A Boeing 747 made of steel would weigh 1,200 tons instead of 400. You'd need engines 3 times more powerful, burning 3 times more fuel. But carrying that extra fuel adds weight, which demands even more fuel. The tyranny of the rocket equation makes long-haul flights impossible. Without aluminum, commercial aviation as we know it doesn't exist. Short flights on steel planes? Possible. But New York to London would need 2 refueling stops, turning 8 hours into 20, while ticket prices would shoot up to several $1,000s. Molten aluminum gets poured into molds, forming ingots weighing several tons. Then they're reheated to 850 degrees Fahrenheit and pass through massive rolling mills. The rollers press down with thousands of tons of force, and with each pass, the ingot gets thinner and longer, transforming into sheets ranging from 0.02 of an inch to several inches thick. Rolling aligns the grain structure, locking in specific mechanical properties. Here's where another critical quality emerges: electrical conductivity. Aluminum conducts electricity 60% as well as copper, but weighs only 30% as much. Every high-voltage power line uses aluminum around a steel core. The aluminum conducts the current while the steel carries the load. If we had to use copper instead, the wires would be 3 times heavier, the support towers would need to be 3 times stronger, and spaced closer together. Building power grids would cost 4 times more. Rural electrification would never have happened, and your monthly electric bill would triple. Every sheet undergoes the strictest quality control, and there's a concrete reason for that. On April 28, 1988, Aloha Airlines Flight 243 was cruising at about 24,000 feet above Hawaii when passengers heard explosive decompression. The entire upper section of the forward fuselage tore away, exposing nearly 18 feet of skin and opening the cabin to the sky. 1 flight attendant was killed, 65 passengers injured. The investigation revealed that the aluminum fuselage had developed microscopic fatigue cracks after years of pressurization cycles. With every takeoff, the fuselage expands under pressure. With every landing, it contracts. Thousands of these cycles, and invisible defects appear in the metal. Tiny cracks grew and connected until the structure failed catastrophically. The aircraft had completed 89,000 flight cycles, and technicians couldn't detect such small defects. This tragedy completely transformed how the aerospace industry inspects aluminum. Today, every single sheet goes through eddy current testing, which detects surface cracks as small as 0.004 of an inch deep, ultrasonic testing that finds internal defects, and X-ray examination for critical components. Plus fatigue testing, Samples get bent millions of times, simulating decades of flight cycles to verify the alloy's reliability. The rejection rate for aerospace aluminum is 12%. Every eighth sheet fails inspection and gets sent back for remelting. That number seems high, but after the Aloha disaster, the industry decided, better to lose metal than lives. Aluminum that passes inspection goes to manufacturers, who turn it into everything, from aircraft to soda cans. A major plant produces around 300,000 tons annually. And virtually all that rejected metal doesn't go to waste. Aluminum can be remelted infinite times without losing its properties, and remelting takes just 5% of the energy needed for primary production. Without aluminum, cans would be made of tin-plated steel, weighing 3 times as much. A 12-pack of Coke, 24 pounds instead of 9. Shipping costs triple, prices double. Construction would look completely different. Modern curtain walls use aluminum frames, strong enough for glass but light enough that buildings don't need massive reinforcement. Without aluminum, tiny windows in thick walls, or steel frames so heavy that buildings over 50 stories become impractical. Modern glass skyscrapers don't exist. Computers and smartphones would be different too. That aluminum laptop body would have to be plastic or magnesium. Plastic isn't rigid enough and cracks. Magnesium is light but catches fire during machining. The plant's been running for over 120 years, producing roughly 20 million tons of aluminum, turned into planes, cars, buildings, power lines, packaging, and electronics. Without the electrolysis process running in those reduction cells, none of this exists. We'd be trapped in a world that's heavier, more expensive, and far more limited.
Every year, the world produces over 500 million tons of glass. Without it, there'd be no windows, smartphones, cars, or skyscrapers. But few people know that the journey to this perfect transparency doesn't start with glass at all. It starts with hot sand, heated in furnaces to temperatures exceeding 1,600 degrees Celsius. This isn't just manufacturing, it's modern-day alchemy. Millions of tons of sand transformed into an ocean of molten glass, floating on liquid tin to create a perfectly smooth surface. You're about to discover the secrets of this process right here. Before hot sand becomes a transparent window, it all begins in a quarry. The primary raw material for float glass is high-quality silica sand. It must be almost perfectly pure, with a silicon dioxide content exceeding 99.5%. This sand is extracted from special deposits, typically deep underground. One of the most prized is Ottawa sand from Illinois. Pale white, fine as flour, and exceptionally pure. Quarries operate like giant anthills. Excavators tear through layers of earth, whilst lorries, 40-tonners, haul the sand to crushing plants. Then comes dry screening. The sand is cleaned of stones and the slightest impurities. Besides sand, glass contains several other components. Soda ash lowers the melting temperature. It's transported from salt deposits, particularly from Wyoming, in 23-kilogram bags or in bulk. Limestone stabilizes the structure. It's supplied from quarries and ground to a dust with particles under 1 millimeter in diameter. The mix also includes dolomite, aluminum oxide, saltpeter, and glass waste, what's called cullet. Cullet reduces the energy consumption for melting by up to 25%. After initial cleaning, all components are mixed in precise proportions, which are kept as trade secrets. A giant mixer the size of a 2-story house prepares the glass flour mixture. The finished mixture is transported to production by lorry and sometimes by rail or even on barges. Storage temperature must be controlled. no moisture whatsoever. The warehouse resembles a sterile grain elevator with silos, each with a capacity of roughly 560 cubic meters. The mixture is then automatically fed into the glass furnace, where within just minutes, everything that was sand and dust yesterday transforms into a boiling ocean of glass. The mixture enters the heart of production, the glass furnace. It's a genuine industrial volcano, over 60 meters long, with temperatures reaching 1,600 degrees Celsius at the melting core. Raw materials are fed in automatically, several tons per hour. In the first 9 to 12 meters of the furnace, melting occurs. Components melt and merge into a glowing, viscous mass. Next comes the homogenization zone. The mass is stirred and matures until all bubbles and lumps disappear. And only then does it gently flow onto metal. This is where the magic begins. In the second stage, the mass enters a bath of molten tin heated to 1,100 degrees. The glass literally floats on the metal, spreading into an even ribbon. Thanks to surface tension and the perfect flatness of the tin, a mirror-smooth surface forms on both sides, without polishing, without presses. Thickness is controlled by stretching, special rollers, or electromagnetic fields either stretch or compress the glass ribbon. This way, the output can be glass ranging from 1.5 to 19 millimeters thick. The tin bath spans over 45 meters, and the glass slowly floats along it at speeds up to 7.5 meters per minute, cooling en route to 540 degrees Celsius. This is an absolutely critical moment, but even at this stage, it's not ready yet. Next comes the annealing zone. The glass ribbon passes through a long tunnel where it cools by several degrees per minute to relieve all internal stresses. Without this, the glass could later crack on its own. Its surface is like ice, smooth without a single scratch. The sheet size is impressive, up to 3 meters wide and over 9 meters long. In this state, the glass enters the cutting zone. Before it's cut, a computer scanning system analyzes the entire surface, searching for micro cracks, inclusions, stress points. Any find means that sheet's rejected. Cutting isn't mechanical anymore. Now it's laser or roller scoring. A microblade, similar to diamond, scores a line, and then gentle pressure snaps the glass precisely along that path. Sometimes sheets are cut straight to order, say 60 by 90 centimeters for construction glass or screen size for Tesla. Others go in standard formats to warehouses, where they're stored vertically on racks with rubber spacers. After cutting comes the calibration stage. Sheets are checked for thickness, geometry, straight edges. High-definition cameras scan every centimeter. Lasers analyze the corners. There are almost no human hands here, only at the final stage when workers in gloves mark the perfect sheets. In a world where glass has perfect transparency, marking is its name, passport, and craftsman's signature all in one. It's in the marking zone that each piece of glass is given its identity, where, when, by whom, and for what purpose it was created. The most common method is laser engraving. A special laser burns microscopic dots onto the surface, creating an indelible frosted inscription. Font thickness is less than 2.5 millimeters. This inscription can't be removed without damaging the glass, which is precisely why it's often used as an anti-tamper code. Sandblasting is used for decorative or premium glass. Through a stencil, abrasive is applied to the glass under pressure, forming a raised frosted mark. Then there's marking with ceramic inks. This method is used at the stage before tempering. Special paint is applied by printing, then baked at temperatures exceeding 1,100 degrees. This marking is colored, noticeable, and extremely durable. It won't wash off, won't wear away, and won't fade. Marking can be either technical or branded. For instance, windows in luxury homes often proudly display the manufacturer's logo. In some projects, marking is even used for authenticity verification. For example, glass for armored vehicles or government buildings receives a serial number in QR code. The final stage is documentation. Every sheet gets a record in the system, like in a hospital. What sort of patient it is, when it was born, what properties it has, and where it's heading. This matters because glass isn't always dispatched immediately. Some batches are stored for months until their time comes.
The Caterpillar 3618 engine, 18 cylinders, 88 gallons of displacement, 7,200 kilowatts of power, 9,655 horsepower. One engine weighs 79,000 pounds. The piston in this engine, 11 inches in diameter, 11.8 inches of stroke, 50 pounds in weight. This is Caterpillar's largest piston. How do they make it from liquid aluminum? Today you'll see the complete production cycle of a giant piston, from an aluminum ingot to a part that moves at 33 feet per second and withstands 2,685 psi. If you want to see how they make the heart of a giant engine, subscribe to the channel. Here we show you the factories that move the world. The Caterpillar 3618 engine is designed for high-speed marine vessels, ferries, patrol boats, yachts. A single engine produces 9,655 horsepower at 1,050 revolutions per minute. It's a V18 four-stroke diesel. Cylinder bore is 11 inches. Stroke is 11.8 inches. Displacement per cylinder is 1,130 cubic inches. 18 cylinders total. 20,330 cubic inches. Compression ratio 12.6 to 1. Maximum cylinder pressure 2,680 psi. That's 185 atmospheres. Combustion chamber temperature 3,600 degrees Fahrenheit. Mean piston speed 34.4 feet per second. The piston travels 11.8 inches in 0.028 seconds. Up and down 1,050 times per minute. 70 million cycles over 10,000 hours of operation. The piston material has to withstand all of that. The piston is made from an aluminum alloy. Aluminum is lightweight. Density of 169 pounds per cubic foot. That's 3 times lighter than steel. Aluminum conducts heat well. Thermal conductivity of 133 BTU per hour per foot per degree Fahrenheit. That's 5 times better than steel. They use alloy 2618. Composition: 92% aluminum, 4% copper, 1.5% magnesium, 1% nickel, 1% silicon. Copper provides strength at high temperatures. Magnesium increases hardness. Nickel reduces thermal expansion. Silicon improves casting properties. The alloy arrives in ingots. Shape: a cylinder 12 inches in diameter, 3 feet 3 inches long. Ingot weight: 353 pounds. Before forging, the ingot is cut into blanks. Blank length: 12 inches. Weight: 84 pounds. This is the blank for one piston with extra material for machining. The blank gets loaded into an induction furnace. Temperature: 895 degrees Fahrenheit. Heat